3 probando. 1, 2, 3.
but they haven't shown yet. Uh, so that's why we are a little bit delayed. We are transmitting live in the YouTube channel. If you have friends or family that you would like to see you during your presentation, please. We sent we did send the link. Share it with your friends. So we will the dynamic will be the presentations. We will give some time for questions, but we will have questions through the YouTube channel. In the room, in the technical room over there, we have a person that will be summarizing the question from the YouTube channel. So you might hear a voice asking a question, and you probably won't see the person talking. So that's our guy over there. So I would like to invite the Chancellor of the University to give a few words.
Good morning to all. It is a pleasure to be here. I understand this is the 37th IAP Spring meeting. And I was talking to Dr. Raul Torres and the other people that are in charge of the organization. And it's impressive the amount of activity that has been generated this year. Just to give you a few numbers, I just learned these numbers a few minutes ago. We have 35 projects. I think this is a huge number. We have 174 students participating, and we all know that all of these activity started within the electrical and computer engineering department. But I also found out that there are students from even other departments within engineering, but also from arts and sciences. So I think this is being spread, the initiative, to many places. And I feel very, very, very grateful of everything that has been done. I would like to thank the sponsors. But I know this is being watched somewhere else. We need more sponsors. We need you to put the money where it will have return, a very good return on your investment. This is an activity where you will promote students doing things outside of the classes, the classrooms. Most of the activity is related to undergraduate research. So this is a very important investment. And I am sure that many of these students, at least the ones that distinguish themselves more, will become your employees. And you will have a chance to know them, see what they can give. And I'm hoping that some of you students here will get very good offers from many companies, but we need more companies to invest in this very important activity. But I think it's an excellent result that we have this year. I encourage you to keep participating. To students, if you like research, consider graduate studies. Particularly in engineering, we have graduate programs, master's and PhD programs in practically all of the engineering disciplines. The only one that we have that has not been established yet is industrial engineering, but we have a letter of intention. So that's the commitment is there, and it's going to go through all the channels to have very soon a PhD program in industrial engineering. Also, as all of you should know, if you don't know, please listen. This year we were informed that we obtained the classification from the Carnegie Foundation as an R2 institution. That means that we are a high research activity and a high PhD production institution. And this is an elite group of universities, and now we belong to that group. So to keep belonging to that group and to set our target on becoming an R1 institution very soon, we also need students to get involved in research and eventually getting PhD degrees, but because those are the two key metrics. How many PhD students we graduate and how much money we spend on research. Those are the basic two metrics. Everything else is a consequence of having those numbers as high as possible. So students, I congratulate you. I saw the agenda. You will have your opportunity to give your presentation, give your pitch. See this as a pitch. You have to show what you've been doing and convince those who are participating that it is worth participating in the Industrial Affiliates Program. Dr. Raul Torres, congratulations for your consistency, for your persistence, and for many years being there as the leader of IAP. So keep up the good work. We appreciate and we value your contribution. So thank you very much. I hope you have an excellent day.
Thank you, Chancellor. Now we have a few words from the Dean of Engineering.
Buenos días. Otra vez. Buenos días. Fantástico. Good morning. As Dean of Engineering, I'm really excited to be here and celebrate together this fabulous event. This is important for me because a year ago I started my process as Dean of Engineering, and this was the first activity I had the chance to celebrate with the community, saying a welcome as Dean of the College of Engineering. I joined the Chancellor, congratulating all of you in this fantastic event that for 37 years showed the resiliency, innovation, creativity, and support of a community. Together we join industry, mentors, many of them who have been alumni from our College of Engineering, and we're very proud of that. Also the faculty. Faculty are very important, serves as mentors to develop the skills to push the students a little bit harder to achieve new goals and develop the skills, the knowledge, and the abilities to be able to attain the goals that we have out there for the industry. Also for you students, enjoy this moment. You've worked for a year, really, really hard. Trial and error, creating new things. You failed probably many times. But in this process today, you'll be sharing the accomplishments, the objectives that you've reached. So more than just giving a presentation, you're doing a pitch, as the Chancellor said, but you're also celebrating the accomplishments that you've achieved during this full year of hard work. For the industry mentors, thank you. I wish there were more in the room. I know there's many limitations now for travel, but we value your support, we value your commitment, we value your mentorship, because it's important. And for all these students that are here in the room, once you graduate, I'm giving you a task. I'm giving you a challenge. The mentorship you received, you'll give it back. You'll come back in a few years, and you'll be the mentors of the future generations of students. So that is my goal for you. As the Chancellor invited the companies to give back, to give and to support our initiatives of innovations, I am challenging you all and those back in the YouTube channel to come back, to celebrate, to be part of our community and make the University of Puerto Rico Mayagüez campus and the College of Engineering strong, stronger, together for future generations. Have a fantastic 2 days of presentations, of sharing and growing and learning, and celebration.
Yeah, we also have the Dean of Research and Development in Engineering, Heidi Sierra, please come.
Good morning. As a Associate Dean of Research of the College of Engineering, I welcome you to the 37th Industrial Affiliates Programs meeting. This event reflects the growing relationship between industry and academy at UPRM. This relationship is important to grow research, to create innovative technology, and to provide the students opportunity to meet the real challenges in the world. The College of Engineering is committed to foster new opportunities for collaborative partnerships that benefit our students and our partners. To all the participants, mentors, faculty, and students, and organizing committee, thank you for making this event possible. I hope you have a happy and fun and very, very productive meeting.
Our next, we have a talk, the Center of the Advanced Radio Science and Engineering Research, Education, and Industrial Collaboration. I would like to present you with Dr. Rafael Rodriguez Solis. He received a bachelor degree in electrical engineering and another bachelor degree in computing engineering from the University of Puerto Rico at Mayagüez campus. His master's is in electrical engineering from the University of Florida, and his PhD in electrical engineering from the Pennsylvania State University. He is currently a professor of the electrical and computer engineering at the University of Puerto Rico, Mayagüez, where he served as the director of the NSF Center for Advanced Radio Science and Engineering in Church Carse, the UPRM Microwave Antennas and Remote Sensing System Laboratory in Church Mars, and the Institute of Research in Integrated System and Engineering in Church Irise. He also served as the coordinator of the RF System Laboratory and the ECE graduate program, and is a researcher in the Spectrum X, which is an NSF Spectrum Innovation Center, led by the University of Notre Dame. He received the NSF Career Award to work in the characterization of wideband slot-like antennas, and a NASA Glenn Summer Research Center Faculty Fellowship to work in the development of microwave and millimeter wave antennas using polyimide aerogels. He worked as the UPRM PI for the NOAA Collaborative Science Center of Earth System Science and Remote Sensing Technology, and as a researcher with the NASA Tropical Center for Earth and Space Studies, the NSF Center of Surface Sensing and Imaging System, and the NSF Center of Adaptive Sensing of the Atmosphere, CASA. He also received the Advanced Research Grant from the Puerto Rico Science, Technology, and Research Trust to work in the development of the UAV-based compact radiometer to measure sea surface salinity. Dr. Rafael Rodriguez Solis has been selected as an outstanding professor in electrical engineering by the UPRM engineering faculty in 5 separate occasions, and as a senior member of the Institute of Electrical and Electronic Engineering and the International Radio Science Union. He served as a chair of the 2025 IEEE MTTS Latin American Microburst Conference held in San Juan, Puerto Rico this past January, and as a general co-chair of the 2016 IEEE International Symposium of Antennas and Propagation held in Fajardo, Puerto Rico in June 2016. Dr. Rafael Rodriguez Solis' research interests include wideband microwave and millimeter wave antennas, reconfigurable, tunable, and multi-band antennas, wideband and tunable microwave circuit, and microwave and millimeter wave remote sensing system. With great pride, I would like to present you then and leave the floor to Rafael Rodriguez Solis.
Thank you, Raul. Good morning, everyone. Let's see if I can bring this up. So I would like to talk a little bit about what we are doing in our in the Center for Advanced Radio Sciences and Engineering. This center started a couple of years ago. So I will start. So I will give you a small introduction on the program and some highlights of what we do in the center, and go through some specific projects to give you an idea of what we are doing and try to get some interest from you in participating in our center. So just to talk a little bit about me, Raul gave a short bio of my background. I did my high school in public school in Carolina, and I came to UPRM, where I got my bachelor in electrical engineering and computer engineering, and then went to Florida for my master's and to Penn State for my PhD. Here at the UPRM, I'm working as the graduate program coordinator in the ECE department, and I'm the director of CARS and of our microwave laboratory. And as he mentioned, my interests are mostly in antennas in microwave frequencies. So why are we working here in CARS? What do we want to do in CARS? Why are we doing this in here? So one of the issues that we have is using the spectrum in an appropriate way. And we have receivers that are very sensitive and do work for us every single day, and we don't even know about that. When we do weather forecasting, for example, we have a number of satellites that go around the world every day, taking data, basically just reading what the radiation from the surface of the ocean, from the surface of the land, from the atmosphere itself. And we use that information to do our weather forecasting, to do climate models, and so forth. At the same time, we have other people that are looking into the stars, doing radio astronomy, have very, very, very sensitive receivers that are getting radiation from stars that are very far away, and you need receivers so sensitive that are basically working at the quantum level. And in the world and the United States, for example, we have a number of, let me see, we have the spectrum divided into many different uses. You want to have all these different squares here that indicate what the applications are for, and the frequency these applications are used for. And we want to stay in that small square, in that small band, and try to not interfere with the rest of the people, but it so happens that as perfect as you want to make things, you can have some spillover from your signals to affect other users. You want to minimize that, but sensitive receivers, scientific receivers, cannot defend themselves usually. So we have now radars that want to follow up your airplanes and can interfere then with the satellites that are taking data from the Earth. You have cell phones. You have your cell phones and cell phone towers that are also emitting information that will just get scattered, and they will also be captured then by those satellites that want to get information from the Earth. You have radio astronomy receivers. You have microwave profilers that are trying to get information from the sky, and then they get interfered, some by the emissions from your close-by users, but at the same time from other satellites that are transmitting information. Like, you have all these satellite constellations that want to communicate with giving internet services and provide cell phone services as well. So for that reason, we created CARS. This center was started in January 2022 as a cooperative agreement with NSF, and it's a collaboration between UPRM, the University of Central Florida, and the National Radio Astronomy Observatory. Our mission is to enable the development of integrated tools that can solve these interference issues with scientific receivers in particular, and we can also to improve the performance of those receivers to improve the radio science observations. And we want to do that through the creation of a diverse community that is interdisciplinary and is inclusive to all that participate on them. And as a vision, we want to become a center of excellence that can build local capacity, infrastructure, and the future workforce in radio sciences and engineering disciplines that can make this happening. We have basically 3 cores in CARS. The most important one, the education, outreach, and workforce development. We have a research component that will put together all these activities, and then we have an innovation and collaboration ecosystem that we use to collaborate, to expand collaborations outside the university. Our team is large. We have about 12 faculty and 20-some students or so from the faculty, and postdocs are from the electrical and computer engineering department and from the physics department at UPRM. And from the English department as well, our colleagues working with us with the education and workforce development areas. So we have, as I mentioned, 3 postdoctoral associates and 12 faculty, about 13 graduate students at some point, and 20 undergraduate students working on different projects, and we have also center staff helping us out with all the administrative procedures. So let me start talking a little bit about the education aspects of the center. So we wanted, when we started this center, we wanted to make it a little bit different than what we have been doing in other projects before on campus. We usually want to pick up the students that are the best and the brightest from when we go and do outreach. And we said, well, you know, there are some populations around that have very, very good students, but we just don't go and look for them. And we have and I always say this, and I will say it every time I step on any platform, I will say this, that my favorite program in this campus is the Center for University Access. They go to the local schools and look for these first-generation students, low-income students that are our neighbors, and they don't even think that the university is a possibility for them to continue in their careers. So they go and bring them to the campus, show them what we do here, give them tutoring for their classes, give them tutoring for the College Board entrance exam, and and help them out with the application for university. And some of them apply to UPRM, some others apply to other universities. Those who apply to UPRM and come to study here, they keep them mentoring, and they make sure that these students graduate. And they use them as mentors for the students in middle school and high school. And this program, it's been, I think now 17 years running. When we started the center, I said, you know, we need to bring them together, bring them to work with us, because this is the way that we can really make an impact to our local community here, and we can then bring another population of students that we don't usually work with us. So we have been working with them since we started, and they have a summer camp that they have for about a week, bringing students from the area, about 40 students coming into campus working that. And they, as I said, they help foster university aspiration for those students. We are working together also with the National Radio Astronomy Observatory. They'll help us out building up their proposal when we started, and we have been bringing students from some of their programs into UPRM during the summer, usually 2 or 3 students from their partner universities. And we have been we had the opportunity to send one of our students out as an undergraduate co-op for a semester this past year. We've been working also together with NASA. We had a student who went to NASA, and we've been trying to make projects with them in terms of radio wave propagation activities. And we have also working with the Spectrum X Center from NSF in other educational activities. And for our students here, we've been bringing some different fellowships, supplements from NSF. We have been working on curricular sequences to expand the education opportunity for our students over here. And we have a student leadership council that has been really active on making a student community and give that sense of community to the students to move forward. So to show you some of the activities that we have been doing with the summer with the students, we bring them here. We have some of our own UPRM students working for us during the summer as well. So we take them to the Parguera so they can see the bioluminescent bay, and we take them out to do kayaks, and we take them out to this was, I think, in El Bosque del Pueblo in Adjuntas. Take them out. So besides the work that they do in our labs, we also take them out so they can see a little bit of what we do of what we have to offer in the island as well. Dr. Leida Leon is helping us out with the educational component, and she was working together with our partners in Spectrum X, and we had together like a summer school and wireless hackathon. We have like 20-some students, about 20 students here, about 12 students here, I think was this, in our campus, taking this, just making some measurements in wireless, so I show them the basic of wireless, how to get the signals, intercept them, and so forth. As you can see, and this was led by Dr. Maria Sheleva from University of Albany. And we had, this is the 3rd time that they do it. The first time they do it multi-campus, and beside us, there were also Florida State University and University of Hamilton. UPRM and Albany were the ones that had the most amount of students participating in the hackathon. So we are planning to do that next August again. So keep in touch, so we'll let you know when the days are going to be. So we are participating with our students. We have get our students to participate in some of the workshops for the QUAS students. And we have some mentorship for the REU students as well. We have, as I mentioned, this hackathon. We take them out to an activity called Spectrum Week. We have so many different programs from NSF related to Spectrum, and visit them. And we take the students to present their work and have a visit over there. Internships, fellowship, and assistantship, so we can have that for the opportunity for our students to participate in the program. And this is some of the highlights as well. We have some of our students participated in the summer to launch a number of radiosones during a week, so we can gather some information on the local conditions, on the local weather conditions, to help out our the validation of the data we get from our microwave profiler on campus. So I'll talk a little bit about the research that we do in cars. We have a structure of 3 components. One of it is what we call R1. We work in microwave and millimeter wave systems, and there our idea is to build platforms that can measure and monitor spectrum, and can develop a monitor system that can be of dual use and improve the sensitivity of the receivers, of the scientific receivers. R2 is what we call reconfigurable computational structures for signal processing. This is basically building hardware that can be reconfigurable, can be reused. So we build algorithms to analyze the signals that we obtain, so we can extract that interference and get more cleaner observations. So from the monitoring, for example, system that we use in R1, we can use those results and plug them into the algorithms developed in R2 and in the hardware developed in R2 to get them a better understanding of the signals. And then we have what we call cross-cutting and applied radio sciences. We have a team of faculty from physics working in radio astronomy and working in atmospheric sciences. And they have their own problems. They are doing their observations of the atmosphere. We have a microwave radiometer, as I mentioned, here on campus in the physics building. We have found that there is some interference in there. How can we take that interference out to improve the forecast that they do? How do we understand what the effect of that interference is on the forecast that they can do from that? And from radio astronomy, there is our team had the opportunity to participate in the commissioning of a 12-meter antenna at the Arecibo Observatory, and they took a lot of data during that commissioning before the observatory closed. And they found a lot of data there that, unfortunately, was contaminated by radio frequency interference. So what techniques can we use to eliminate that interference from those readings so we can get more data and we don't have to eliminate that many data? Those are the problems that they bring, and we try to bring solutions through these 2 other trusts, or by the work that we can do together between them. So to give you an example, so far in R1, we are concentrating in doing multifunction arrays. We're trying to do antennas that can do at the same time communications and can do sensing. So we're looking into the antenna aperture, how can we design those, design that array so it can provide both functioning without interfering with each other. We're looking into the RF front ends, how can we define the amplifiers, mixers, and so forth, so we can get better signal. We're looking into interference suppression, looking with on designing amplifiers that have integrated filtering techniques that we can reduce the interference that to the desired signal. And we have 6 undergraduate teams. You may see maybe 3 or 4 of them actually at IAP, showing some of that work as well. That we train them on the use of different design software, the use of SDRs, using different microwave instrumentation. So, one of the focuses of the project so far is working at Ka band, so working from 20 to 30 gigahertz. Basically, because this is one of the bands that the radiometer that we have in physics works at, and we've been then looking into doing electronic scanning, so we can do some type of spatial filtering. If you point your antenna to a particular place, you can then look away from where the interference comes from. And thereafter we have a very high gain, so we can improve the sensitivity to the intended signal. And we're trying to base this on current commercial 5G technology. So we had chips that can do the beamforming, so we're trying to use those chips and to support the work that we're doing right now. So we don't start from scratch. We already have a platform that we can start using that system from. And this is suited for spectrum monitoring and doing micro radar systems. So some of the work that we have been doing is the development of these antenna elements and going from the antenna element to the design of the full array. We're also working now into the down conversion and then how to work on this digital transceiver, how we get all that signal and get them together and get it together so we can extract the information that we want from the array. We have been working also on the development of amplifiers at very high frequency, of not just amplifiers, but the whole front-end system includes the amplifier, includes the mixer, includes an oscillator, and the development of that so we can make very small receivers to monitor the spectrum. And if we can say that we can bet that if we can get these receivers very small, we can just throw them around. And instead of having a very sensitive receiver in one place, we can try to see if we can have the same capabilities with maybe a less capable receiver, but many of them thrown around so we can get a better, the same, or at best as good as a result of having just one very, very sensitive and expensive platform. So, as I mentioned, one of the projects is to try to get some filtering capabilities to the amplifier design itself, and this is what they call a winner-takes-all filter that will select which level of the signals you want to get. If you want to eliminate the very high peak signals, you want to eliminate the very low signals, so depending on what you want, you can program the filter to get that and can help you out in eliminating the peaks or spurious signals that get into your system and reduce the amount of data that you need to eliminate because of the saturation, because of this interference. At the same time, because they need to have a very fast transistors to work into this, they're looking into super transistors configurations to the design of these low noise amplifiers and for these filter applications. Some other teams are working into propagation studies to see, well, what can we do then to improve, to understand how the signal propagates through the air, through different medium, and this will help us also train the students in different techniques and tools that they can use then later on in their careers, like software-defined radios. And in terms of the capacity building, infrastructure building, we had the opportunity to set up a near-field measurement antenna system, a planar antenna system. We're putting this together with Dr. Rafael Medina. This system will help us measure antennas from around 4 gigahertz up to 67 gigahertz. We have another system that works up to 40, so this will give us another capability in the laboratory to improve those measurements. And this is all being built in-house. The system, we just bought the parts for this frame that we see here. The professor and students are building the software to get the measurements from this antenna system to get, and then to extract that information to measure the radiator patterns. The second group, we call R2, is looking most, as I mentioned, in digital digital hardware, digital reconfigurable hardware. So looking into FPGAs, for example, and looking now the processing of the signal, what we call the digital backend. Once we get all the analog information and we process that as much as we can, then we go to the digital part. We do whatever filtering, whatever processing we can in the analog domain. Now we make the life easier in the digital domain. And we're looking for different strategies for real-time mitigation of the interference. For example, if we have antennas that can measure the interference around a very sensitive receiver, we expect that that receiver will get not just the data that we want, say that's radio astronomy information from that star or that cluster or that pulsar, but also will capture that interference as well. These receivers we expect that are not as sensitive. So they will not see much of that pulsar, of that star, or that cluster, whatever. So this will mostly capture what we have as the interference. So if we can combine this with this, we might be able to reduce, to subtract, or in some way mitigate what this is seeing in terms of the interference. So that's one of the ideas that we have that we're working with in these past years. We're putting together a test bed to do that, both here and with the University of Central Florida. And we're looking at post-processing techniques as well as real-time techniques, and using machine learning techniques also to do this RFI mitigation. So we're looking for different adaptive filtering techniques. So we decompose the signals to do this adaptive filtering, and we got this architecture of hardware that we can process the signal in many different ways and then select the way, depending on the signal of interest, which way is easier or is more appropriate to reduce the interference. And then we get this feasibility to see how we're able to get out of the interference from the signal. So we get this, our input main signal, the one that have the RFI, and we decompose those two and start to make some different filtering until we get only the data that we want in the end. Now, this is a picture of the hardware I'm putting together. This is like a small GPU cluster with the CPU and what we call an RF SoC. This is RF system on chips. It's a very capable system that can get basically signals. In our case here, can get signals up to 6 gigahertz directly sample. You don't need to have a down converter for that. So we have different signal generators also to do some synthetic processing and spectrum analyzers to test what we are doing. So with all these servers and whatnot, we can then our astronomical signal from one place, the reference source from another, and to the RF SoC start doing that processing using their FPGAs, so with the programming of the FPGAs here, and the GPU. One of the latest news from the center is that we were able to get NRAO to provide us with 2 sets of data. We were planning to do this with the 12-meter antenna at the Arecibo Observatory, but there is not much access to that at this point. We are working on that with some of our team in the physics department to get access to that antenna. But in the meantime, NRAO provided us with 2 sets of data of their Green Bank telescope and a 20-meter antenna they have there, and we use those to get simultaneous measurements, so we can use that and test our system with actual real data in a setup that was intended. And these are some of the tests that we have developing. For example, we can see like the signals and the different interferences that we can put in there, and then we can just play with that and try to eliminate the interference, identify and then eliminate the interference that we find in that we introduced. With the radiometer that we have, we know what type of signal we are expecting in this band from 20 to 30 gigahertz. In that band, we're basically measuring water vapor. And the water vapor, the absorption of water vapor takes a signal, a shape like this. And we find that many of the channels were kind of contaminated. We were receiving this spike in here around 28 gigahertz. That's basically a 5G station that is transmitting nearby campus. So how do we take that out so we can use the whole profile? We see we use the whole profile. So our student has been working on auto-encoder approaches, so we can then try to, knowing how the interference looks, how our profile should be looking, how do we eliminate that from the signal. From our cost-cutting and applied sciences team, as I mentioned, this is a picture of the radiometer that we are using at the physics building. They have been working on identifying what's the atmospheric capacity in the region and for the boundary layer prediction, and we'll talk a little bit about that. And the radioastronomy group is looking into the interstellar, looking into the galactic interstellar medium, doing radio spectroscopy, and doing RFI mitigation with different statistical methods. So atmospheric opacity is basically how opaque the atmosphere is to the electromagnetic spectrum. So what you are, for people that are looking at radio astronomy, they are looking to electromagnetic signals coming from the sky. If the atmosphere is opaque, it means that you cannot receive anything from those electromagnetic signals down in your telescope. So if you understand how opaque that atmosphere is at different frequencies, we can say, well, this is a good place, or it is not a good place to place a radio telescope. That's why you see that many of these telescopes, like the one I showed at the beginning, is put in very high places, very dry places, like in the Atacama Desert in Chile. This is a very, very high place. It's a desert, so it's very, very dry, so you have no atmospheric attenuation from the signal, so you can you can take measurements up to 200 gigahertz, 300 gigahertz. Here in Puerto Rico, for example, in the Arecibo Observatory, they used to go up to 10 gigahertz. Going above that because of the humidity, because of the rain basically every day, you have very small windows for you to get higher than that. So we were trying to see if can we take measurements higher than that. The team here was looking at 24 gigahertz for that, because that's one of the frequencies of very interested for the radio astronomers. So that's one of the oxygen resonant bands. So they were trying to come up with a function, a mathematical function that could describe the opacity at 24 gigahertz as we go up in height from the ground. And with this, then we can say, well, depending on how many days you have with the signal that the atmosphere is less opaque or more opaque, we can decide if it is feasible at a particular location to place a radio telescope or not. This is some of the conditions that you will see, like here in the area. For example, this is Puerto Rico is right around here. So at the very low levels, you see a lot of the Sahara Desert dust coming into here. Now you have more clouds. So depending on how dry, how moist, is how your opacity gets affected at different times of the day or different times of the year. And this is how it starts changing across the different days. Now, the other work that they've been doing is looking into neural networks to predict the height of the boundary layer. And the boundary layer is basically where all the weather occurs. So depending on how thick, how high, or how low it is when you can get the different atmospheric phenomena, the rain, or it's going to be colder, we have rain, or we're not going to have rain, or so forth. So this is important for the people that do forecasting. So they want to understand all these layers. And you want to predict, using this radiometer, how thick this is, how high it is, during the day. And this is, for example, one of the maps of the height of that boundary layer at 12 a.m. in the morning, for example. So you can see this much lower in the center here, so depending on the topology of the island, how this changes. So this is not done a lot in the tropics. This is mostly done in continental areas. So doing this in the tropics, in islands, is something that not many people have done and have a lot of interest in the scientific community. from the radio astronomy part, our faculty here, Dr. Ison Smith, is looking into the interstellar medium in the middle of the galaxy, and that helps in different to answer different questions, like the distribution of molecular gas in the galaxy, how are the dynamics, that form those gas clouds, how those gases interact to form new galaxies and so forth. So that's for them. This is really important. That they were trying to do a galactic map plane to see this interstellar medium. So this is a photo here of one of the galactic center done by this telescope called Meerkat. And what they did was, using the 12-meter telescope, they look at these 9 regions around the center of the galaxy. And the idea was they wanted to measure CH at these different areas. So now that they have this information from Meerkat, they can compare then what the measurement that they did with this telescope with the ones that they have with the 12-meter telescope. So they took a bunch of different measurements at different places, at different areas, looking for these CH signatures to see if they can get, if there is CH present in those areas or not. So they were able to see CH in many of those areas. They found out also a lot of radio interference as well in there. So there's some of the faculty also, they're working into how to extract and identify where the radio frequency interference is and eliminate that data, or to reduce the effect of that interference there. As I mentioned, we have building 2 test beds, one in atmospheric sciences and one in radio astronomy based around that antenna. For the atmospheric sciences one, we did this radiosonde campaign, and we're also using instruments to purposely interfere with the radiometer to understand what the effect of that interference is, and see if we can eliminate the interference as well. And we put together this test bed, and our collaborators in UCF are putting together something very similar to this as well in their campus, and taking measurements around in their area as well. So we were using one of an instrument from Rodi and Schwartz that loaned it to us. We're trying to interfere our radiometer to see if we can get the effects of that interference, see if we can eliminate that, and see what the effect of that interference is in the measurements that they do at higher levels. And we have already completed our digital backend testbed, and as I said, we're trying that now with new data from NRAO. And I will end here. We have our innovation and collaboration ecosystem, and we have this to link our researchers with other researchers in other institutions. We have what we call SPEED projects, and we're giving some of this funding to other University of Puerto Rico campuses in the island to do some projects for us, and that can help them out to start building some of capacity there and submit to other grants. In Humacao, they put together a small teaching telescope through to one of these grants. We have faculty from University of Puerto Rico in Utuado that are doing work in radio frequency interference elimination and cancellation using statistical methods. Another group in Rio Piedras had put together a series of seminars that bring in people from the outside. Another professor also doing other works in radio astronomy. So we're trying to build a community, not just at UPRN, but also outside, that can have so we can have a better outreach to those. Industry partners. We have had the opportunity to be working with L3 Harris for the past, since we started. They have provided some funding for our projects, and we're looking into developing projects with them at this time. Rodi and Schwartz has been also a member from the beginning, and they have been giving us loans of equipment, and at the same time, they also provided us equipment with a very discounted pricing. We had Verizon participating in cars as well, and they gave a very big, I won't say donation, but they started a partnership with the College of Engineering, and they provided about $400,000 in renovations to the microwave laboratories in the department. And that got multiplied by the partnership with Roddy and Schwartz, because we could get instrumentation half of the price, so we could get them twice of the instrumentation we have been able to get them with Verizon by themselves. And Collins has been also working with us. They have one of our students, they gave up fellowship with them to do projects in 5G applications. So we keep working with the local community here, outreaching the other industry. Also government agencies like NASA, we have been working with them on bringing another radiometer so we can do interferometric studies of radio wave propagation. We had one of our students go there during the past summer at Glenn Research Center. We have also with other another center called Spectrum X, is an NSF Spectrum Innovation Center. We have been doing some education and research collaborations. And that's the basic team of ICE, or the ICE, just try to keep building on those collaborations. And IAP has been fundamental on that, because we have been able to grow on through those collaborations through IAP to bring them up into cars and make them work for us in a very fruitful way. So with this, I finish up my presentation. So if you have any questions, I'll be happy to answer them.
We do have open the microphone. If you want to ask questions, you can stand up and make a line behind the microphone. I just want to add a few details. We have viewers up to 40 in the YouTube channel. So even though you add 40 people from whatever you're seeing here, that's the audience. So that's good to know. I have one quick question. You will have interference from within the band of different devices because you have to share the spectrum, but you also have interference from the atmosphere. So how would you, when you are doing these studies, how do you distinguish between those two interferences?
So you usually, when in a scientific receiver, for example, you may have, usually because they usually have protected bands, so you usually are looking into areas where no one else should be transmitting. Radio astronomy is kind of different because they look at a very, very wide bandwidth, and they usually try to put their telescopes where no one else is transmitting. Now, even when you have these bands where you're not supposed to have any transmitter, you have intentional transmitters are not there, but you have what they call unintentional transmitters. And what happens? Then you have, usually your neighbor will behave more or less okay. You have these filters that will try to, you will see a little bit of a tail of that interference there, but you may have harmonics. And for example, then you have twice the frequency, and that usually is not that well controlled. For communications applications, that's not usually an issue, but for these receivers, scientific ones that are so sensitive, you start getting those harmonics in there that will destroy completely your data. So how you deal with that is very difficult. How you distinguish them, usually you have, to determine if you use a signal, it is from what you're looking at, which is usually noise for these applications. It's just basically, usually when you're looking in atmospheric sciences, you're basically looking like noise. It's like whatever emission is from the air, it looks like noise. Radio astronomy, sometimes you have like pulsars, you're looking for a particular the signals that are in there. So it might be, so you have some pattern to that. But the other signals, the interference, usually modulated signals, you know what type of signals they are because you know if they come from a radar, if they come from a cell phone system, or some other type of communication system. So you might be able to identify where the signal is come from, and that could be used to help into the mitigation because you can kind of identify what type of signal it is, then you know that this is not what you're looking for because they have this type of modulation or this type of behavior that is not expected in the signal you're looking for, or the noise you're looking for, because sometimes you're not even looking for a signal, just basically looking for something there.
May I? Yes. Just thinking about the community that's out there, and you've talked about problems and projects that are multidisciplinary in nature. You're talking about physics, engineering, and other sciences. What opportunities are out there for our students, and what pathways can they go through as electrical engineers or computer scientists that we offer so that they can prepare themselves in this field?
So right now we have opportunities for undergraduate research. As I mentioned, you will see some of these students that are working in cars. We encourage them also to participate in IAP. So you will see some of those students participating in cars that will present some of the work they're doing there here in IAP. Of course, for many of these projects, we don't really need the funding that IAP gives because CARS is already funding them. So we just want the student to have another venue for them to present their projects. But this also gives some type of structure. So participating in this type of undergraduate research projects is like the best pathway to get into what we're doing in the center, because that brings them directly then to graduate student projects and on other type of opportunities. Our professor in physics, she's a new hire on campus. She has I think about 15 students working with her in radio astronomy, working in different type of data analysis type of systems. So students in physics want to do that because of the radio astronomy part, but students in computer engineering, computer science, software engineering, but that type of knowledge is really important for them to get that data science, how do you interpret that data and to get to process those signals. There are opportunities in there.
Well, thank you very much.
Thank you.
We are running late a little bit, but that's okay. We will have our first student presentation of the day. It's field and lab analysis of radio frequency antenna system across multiple spectrum bands. It's Fabián Benítez, Carialis Ramos, Angélica Chaparro, and Yamil Guzmán.
Good morning, everybody. My name is Fabian, and I'm here accompanied by my colleague, Keralis. And today we're going to be presenting a little bit about what we're doing in radio frequency and antenna systems. So without further ado. So a little bit about the agenda. We're going to go, very basic over the objectives, the goals, methodology, a little bit about the results, conclusion, and what we can expect for future work. So for our objectives, we essentially have two main objectives, or two main motivations. The first is the conduction of radio wave propagation studies at essential 5G bands. These bands compose of microwave and millimeter wave frequencies. Microwave being around 1.9 and 3.7 gigahertz, and millimeter wave from 28 to 39 gigahertz. Our second objective is to implement a system that can modulate digital signals using software-defined radio, or SDRs. This specifically is situated for microwave bands, and the ultimate objective is to be able to incorporate both not only propagation studies, but also how does propagating through different mediums affect modulated digital signals in terms of its error bit rate. So some of the goals, we try to study the channel capacity within low, mid, and high 5G bands through different conditions, and these conditions are set either through distancing, transmitter and receiver, adding different obstacles in between recepting antennas. We also analyze the effects of reflection, diffraction, and penetration through different materials. And lastly, we establish a test bench for modulated digital signals propagated at microwave bands. So I'll leave you now with Keralis.
So we use two different methodologies. The first one is the signal propagation, where we recollected the preliminary propagation measurements using some broadband horn antenna for the millimeter wave bands and a directive antenna for microwave wave bands. Then these measurements consist of transmitting just power signals at each frequency band that we are researching under different conditions, such as distance, angle of transmission, lateral displacement, and some signal diffraction. For the second methodology, we have the digital modulation. For this one, we coded a modulation block that can transmit and receive signals using the GNRU radio, which can be used to work with software-defined radios, better known as SDRs. We also used a universal software radio peripheral to propagate modulated signals across a diverse environment landscape and determine the error bit rate. Before going to the results, we wanted to show some key instrumentation that we use for the signal propagation methodology. This one is the spectrum analyzer. This is important because this acts as the bridge between the analog signal and the computer. And since the frequency range is what we are searching for with the 5G, this is the perfect one for our research. Then we use this broadband horn antenna. This is ideal for the millimeter wave bands due to the frequency as well, and here we have some relevant technical specifications. Continuing with the first methodology, we have the effects of reflection, diffraction, and penetration in the absorbers. In our research, these absorbers acted as a free space, mitigating the reflection from the metal table that we use to conduct the different measurements. So in this case, we use only the absorbers with two different frequencies, the 28 and 39 gigahertz. And some of the observations that we made was that we received power significantly reduced at both frequencies, indicating strong penetration loss. We had minimal reflection signal detected. There was no significant difference in received power across different angles, and the higher frequency, being that the 39 gigahertz, showed lower received power. Then, for the key calculations, we observed that the attenuation average for the 28 gigahertz was 45 decibels, and for the 39 gigahertz was 49 decibels. This demonstrates that the penetration loss increases with frequency, meaning that it has a consistent attenuation across different input powers. There was no angle dependency observed, and this overall means that the absorber was effectively mitigating the reflection, diffraction, and penetration as we wanted. Then for our research at the signal propagation, we saw different measurements for the cardboards. In this one specifically, we used 1, 2, and 3 units. That's what's shown in the graphic there. And we observed that the received power decreased as material quantity increased. The small difference in received power between 1, 2, and 3 units shows moderate absorption, allowing partial signal transmission, and there was minimal reflection observed. Then we took only one cardboard and moved it across different angles to see how it reflected or how it shows anything else of the signal propagation, and we found that the received power increased proportionally with the input power. Also, the received power slightly decreased as angle increased, and similar received power was across all angles. Finally, we observed the metal wedge. In this case, we also used 3 different angles, and we found that the received power increased proportionally with the input power, and also decreased as angle increased. The signal detected at higher angles evidence of diffraction around wedge edge or scatter reflections, meaning that it was working well, and that the minimal penetration through metal wasn't there because as it's metal, well, we also expect that it will be reflections. For the calculations, we found the attenuation as well, and we saw that it remains stable across different input powers, and the highest attenuation was at angle 3, meaning that less reflected energy was at wider angles. At the lowest attenuation angle, 1, shows that the reflection directed toward shallow angles was lower. The difference in attenuation angles reflects dominant reflections with minimal diffraction or penetration, and this means that the metal wedge acted primarily as a reflected surface at 39 gigahertz. Now we'll continue with the digital modulation.
So, digital modulation. Digital modulation essentially is a method of being able to transport digital signals across a wide or a very distant, a very vast amount of distance. Digital modulation consists of different techniques, some utilizing different signal properties in its modification. Some use amplitude to represent the binary shifts between 0 and 1s. We can also use frequency and phase. For this study, we utilized the digital modulation technique known as PSK, or phase shift keying. And the reason behind this, well, first, because of its high bandwidth efficiency, and also because it's very common use in applications such as 5G, which is our main objective. So right here we have a digital modulation simulation in the transmitter side. In figure 4, we see a little diagram, essentially the code behind how we essentially took a random source or random digital signal, and we essentially extrapolated it and added it to a carrier signal around 3.7 gigahertz. And this block diagram was actually made using GNU Radio. GNU Radio being a development toolkit that provides signal processing blocks for implementing software-defined radios, which is one of our main objectives, and signal processing systems. It enables users to design and simulate radio systems using software in conjunction with RF hardware, which is essentially our main goal, right? So here, to explain a little bit about the diagram block, right here we have the random source, which is going to be our, let's just say, our data, which then proceeds to, pass to our constellation modulator, which essentially carries that digital signal into our carrier signal, and then these are some the graphical representations. So in figure 3, we see the different graphical representations of said modulation. The first part being the carrier signal, represented in the time domain. You can see that it has like a weird, it's not a pure sinusoidal wave, and it's because it's constantly shifting its phase. Every change in its phase either represents a 0 or 1, and yeah. So this next graph over here represents our actually phase shifting in terms of from 0 to 180 degrees. And over here we have our what we call our root-raised cosine filter, which is essentially the filter that is added alongside the constellation modulator, which essentially determines the bandwidth in which our signal is going to be propagating. Right? And so this is the transmitter side. Onto the receiver side, we can see that in the block diagram, it's a little bit more cramped. It has a little bit more elements, but this is due to us having the previous block diagram, the transmitter side, because what we're essentially doing in the simulation is we're not only modulating the signal, but we're also trying to recuperate it. So this segment right here is this whole block system, all this. And then once it's modulated, we want to, again, demodulate it and then recoup the signal. So it again goes through our random source, then through our constellation modulator, and then it goes to our virtual sync so that it could go to our de-encoder and thus on. So in figure 5, we actually see our digital signal, our RX. It's a little bit difficult to see, but we essentially have our RX and our received and our transmitted signal with a little bit of a delay. Because this is simulated, these signals can be sort of transposed onto each other, and then you can really see whether it would be, from the modulation it could demodulate. So there was an implementation of time delay to see the differentiation. And also, because of this time delay, we can actually calculate the difference in the shifting, and that is what's representing this little spike in below in red, essentially. The last figure represents our shifting between, essentially from a 0 to a 1. And that is all. So in conclusion, the diffraction measurement data showed that the highest power was recorded when the reflective surface was aligned directly with the receiving antenna. As the alignment deviated, a linear decrease in power was observed. Increasing the amount of pressed cardboards resulted in greater penetration loss, primarily due to signal attenuation caused by material absorption. Additionally, the penetration loss was absorbed with frequency increase, essentially. For our future work, we want to continue our propagation measurements using broadband horn antennas with multiple different materials. We also want to continue conducting measurements using PSK modulation techniques and determine error bit rate propagation measurements using our digital modulation. And that would be all for our part. If anybody has any questions, we'd be gladly answer them.
I would like to add a comment for our viewers. There is a delay of about 1 minute or so in the transmission. So if you want to ask a question at the end, please type the question beforehand when you see the video so that we can ask the question at the end. So that's a little hint for the people YouTube channel. Is there any question for the group? Okay, thank you. Okay, we are running late a little bit. So the snacks are already in the Tarzan area. Let's pause for 15 minutes, and then we will come back. It was supposed to be half an hour for breakfast, but let's do it 15 minutes so that we can catch some time for the next group. And because we have viewers in the YouTube channel, we don't want them hanging for 15 minutes without seeing anything. So please, let's have our pause here. Go to the Tarzan area, enjoy the snack, come back, at least the presenters, and feel free to eat.
Yo me lo tengo que bajar bien
Eso es
brutal.
lo que yo le dije a María.
Yo me lo tengo que bajar.
El micrófono está prendido.
Sí, pero me lo tengo que bajar.
No, porque todo... Sí, sí, sí. tú sabes. Nosotros lo usamos cada vez. Déjame chequear. Con esto yo voy a apuntar los equipos. Pues yo no van a tener que hablar, yo lo introduzco. Yo creo que Raúl no tiene que introducirlo. So, wow.
Okay.
¿Cómo yo consigo esa camisa? ¿Cómo? ¿Cómo yo consigo esa camisa? ¿Verdad? Yo no sé. Se pone ahí en la tienda.
El botoncito del medio.
Ese es...
Esto me sale más fácil porque para ahora lo podemos presentar de ahí.
Ahora sí.
Welcome back. We are 15 minutes, we have a 15-minute delay. So we are presenting now design of an SDR-based L-band receiver for AUV-based sea-surface salinity mapping. Our students are Francisco Rossi, Marielis Cuerda, Joshua Rodriguez, and his mentor, Rafael Rodriguez Solis. Welcome.
So yeah, good morning. I am Joshua Rodriguez. I am accompanied by Francisco Rossi and Maria Cuerda, and we will be presenting our research project. So we will be presenting today our motivations, objectives, our goals, our methodology, our results, conclusions, and future work. For our motivation, we noticed that the ocean salinity is fundamental in the understanding of the water cycle and the ocean circulation. So we adapted the Mares team design. They designed a radiometer. So our objective is to implement and change the adequate narrowband filters that it has, and change it to an software-defined radio, or better known as an SDR. This will be our objectives. Like I said, we have to change the architecture of said narrowband filters and introduce an SDR. And to that SDR, we have to implement some new filters. So this will be our goals for the semester. We'll have to gain the understanding of the concept of brightness temperature, identify and understand different radiometer topologies, explore the use of an SDR in GNU radio, and perform the system design of a radiometer digital receiver.
For our methodology, we focused on characterizing the USRP with a signal generator, and we viewed our data using GNU radio. We focused on the frequency spectrums between 1.4 gigahertz and 1.413 gigahertz, and we also measured the error generated in our signal generator using a power meter. Here you can see the USRP that we use in the top left. You can also see the power meter that we use to measure our signal generator. And in the bottom, you can see the signal generator that fed our SDR. Here, these are the results of our power meter measurements of our signal generator. You can see a consistent error of -0.6 decibel milliwatt up until the negative 60 decibel milliwatt range in our signal generator. At that point, the error grows, but we believe that's due to our power meter only being rated to negative 70 decibel milliwatt.
Okay, so here we have our results for our characterization at 1.4 gigahertz. So something that's important to note is that for our characterization, our signal generator, the lowest it could go to was to minus 110 decibel milliwatts. And then in these characterization tests, we varied two parameters. So that was the input power that we could put in our signal generator and the gain that could be applied in the GNU radio little screen that was seen previously in the methodology. So in these tests, we characterized both the receiver and the transmitter port. And in this graph right here, we can see our receiver port results. So the general pattern seen is that for every increase in the input power, so it was around 10 dBm of increase, there was around a 10 dB increase in measured power. We can also see that as the gain increases, the measured power also increases. We can also see that they sort of start out in a stable-like manner, but then for the minus 60 dBm graph, which is this green graph right here, it starts reaching saturation at a gain of about 70 dB. And then for our transmitter graph, we did the same procedure as the receiver port graph. So these three graphs right here are from minus 110 dBm to around minus 90 dBm. We can sort of see that at the low gains from around 40 to 50 dB, these show low sensitivity, and they start increasing in measured power as they reach higher gains. We can also see that, like in this previous graph, from around minus 80 dBm to minus 60 dBm, it sort of reaches a more stable behavior, and it follows the increasing pattern. As the gain increases, the measured power also increases. Okay, and then we have our results here for 1.413 gigahertz. Here we repeated the same procedure. We can see that in the receiver port graph, the same pattern for the 1.4 gigahertz receiver port graph is seen. So the same procedure from minus 110 dBm to minus 60 dBm, and the gain increasing from 40 to 76 dB in increases of around 5 dB. We can see the same linear pattern of increase as the gain increases, and we can also see the same pattern that as we increase our input power by around 10 dBm, the measured power also increases by around 10 dB. And then we have our transmitter port characterization. We can see the same pattern at 1.4 gigahertz where we see low sensitivity at the low gains from around 40 to 50 dB, and then a more linear pattern from around 50 to 76 dB. We can also see that from around minus 80 dBm to minus 60 dBm, the measured power becomes more stable, and the same increase of 10 dB between all of the measured power is followed.
In this graph, we're showing the entire power scale that our signal generator can provide and the entire gain amplification that our radiometer can provide. And we can notice that below 40 gain, we start seeing very low sensitivity at low power ranges. And for our signal generator, we notice that at high power supplied, we start reaching a saturation point. Here we provided a box showing the ideal ranges we want to be working where we don't see any errors with sensitivity or saturation.
Okay, so for our conclusions, with the graphs that were given for our results, we can see that the receiver port becomes oversaturated after the measured power surpasses around minus 10 dBm. All of our results appear to be stable when the power supplied is minus 80 dBm, so it provides the most linear pattern, and the measurements are not affected by the gain provided in GNU radio. So these results mean that we need a gain of around 30 dB to reach the lowest input power that we have on our signal generator, which is minus 110 dBm. And so the available amplifier that we currently have is a MACOM MAL 011078, and it has a gain of 22 dB. So this means that we need this amplifier and potentially another amplifier with a lower gain to be able to supply the whole 30 dB gain that we need. And then for our future work, we want to be able to conduct further characterization tests once we connect the amplifier to the system to make sure that it's actually working. We also want to program a Raspberry Pi to compile the received data of the system once we complete the system. We also want to test the viability of the SDR as a Dickey radiometer or a dual polarized radiometer. And once the system is completed, we would like to run a test to make sure it's actually working. Yeah, thank you for your attention.
If anybody has any questions?
Yes, you have a AUV with a transmitter and receiver on top. Mm-hmm. So you fly it, and you are measuring the salinity of the water.
Yes.
So how the graph that you're showing of power relate to the salinity of the water? Because that's something that wasn't clear.
We showed the graphs with different power levels power level signals being fed to our radiometer because we wanted to see how it would behave at very low power inputs. That's why we concluded that we want to be working in the spectrum we show here. So we calculated that if we would want to measure a signal that's being supplied at negative 110 dBm, we would need around a 30 decibel amplifier to get to the ideal range where the radiometer can observe the signals as expected. Thank you for your question.
Vamos a presentarlos y después que los presento. Our next talk is a study of Penrose tidal microstrip patches from Emiliano Novas and Kenneth Almodóvar.
It's golden here. All right, well, hello everybody. My name is Emiliano Novas. This is my partner Kenneth Almodóvar, and for today we're going to present to you the work we've been doing for the past year. We've been basically performing a study on Penrose tile geometric arrangement and how it could be implemented into patch antennas and maybe turn that into a broadband antenna that could be implemented in microstrip.
So whenever we want to engineer with high-performance applications such as spacecraft, aircraft, or satellite communications, we have to use antennas that are low profile. So that's when microstrip patch antennas come into play. So basically, these antennas have advantages that are low cost, they're very lightweight, and they can be produced in mass in high quantities. But they also come with certain limitations like narrow bandwidth, low gain, and even low power handling capability. And so that is where designs like the proposed Penrose tiling can be utilized. Penrose tiling is a periodic design invented by Roger Penrose in the early 70s. This type of design can be implemented using rhombi with different angles. And the proposed design has a rhombi array to overcome the already mentioned limitations, low gain, narrow bandwidth. So it helps, defeating that. And it also has slots that serve as anchor points. It is because of all these that these aperiodic tiles can be implemented in microstrip technology. So our motivation is just to design broadband antennas and broadband array antennas. That is like the purpose of this investigation, but also the objective is to make this design right there into microstrip technology to see what happens, to see if it defeats the purpose of low gain, narrow bandwidth, and all these limitations. And so for the methodology, we characterize the rhombi, which is the main component of the antenna, and we had two designs, two different rhombis. One of them was 144 and 36 degrees, which you will see in the next slide, and the other was 108 and 72 degrees. Each one of them had sides of 25 millimeters, and a coaxial feed displacement was implemented for the characterization. This displacement was done along the vertical, horizontal, and diagonal axis. And for the characterization, we observed the Smith chart, the return loss in decibels, and the radiation pattern were part of the characterization. And so these are the two designs that we did, and we characterized both, and yeah. So another important step in the methodology was, characterizing the actual antenna. And we characterized the antenna based on impedance and gain, according to not only the feed's position, but also the size of the slot.
All right, so you can see here, I took the ground plane and the patch and I made them transparent so you could see the feed point for the antenna. Essentially what we did was we simulated the antenna multiple times depending on the position of the coaxial feed, because what that does is it changes the input impedance into the system, and depending on where you have the feed placed, it could match the antenna impedance to the port impedance, and that's essentially where you would be operating in. So, but the simulations that we're going to show today are just the ones where we place the coaxial feed at the edges. We have one at a vertical edge, like we place it in the vertice on top, and on the horizontal edge, which is at the x-axis to the right, and then a diagonal where we rotated the patch such that we can place the feed sort of in between those two vertices. And essentially, the reason why we positioned it there is because there you have a better idea of where the antenna would resonate and how and what frequency it would operate when matched and when operating properly. So here you can see the resonances. We had some very consistent resonances for Y and X axis starting at around 4 and 5 gigahertz respectively, and 7 gigahertz for the diagonal edge for the multiple simulations that we performed. We're only showing these three because these are the edge simulations. They're what's most important, and you can see the resonance frequency and the input impedance for these different simulations. And here you can see the gain pattern for the different feed positions. For the diagonal, you can tell that it kind of changes. For vertical and edge feed position, you have a peak gain at 0 degrees, which means that the majority of the energy propagation is happening directly perpendicular to the antenna. So if, say, the palm of my hand was a patch antenna, most of the energy would be pointed directly away from it, versus when we place the feed diagonally, that where it kind of opens up and it shifts. But and we can also see that it has a pretty standard gain for when it comes to regular patch antennas. The lowest that we got was at the diagonal feed, the diagonal feed displacement, which was about 6.4 dB, and the highest was at vertical edge, which was about 8.5 dB. But this one is for this one, I think, yeah, it's for the 108 and 72, which is sort of the wider design that we chose. Now for the narrower design, which is for 144 degrees and 36 degree vertices, these were the results. Again, more or less similar. We have resonances happening between 4 and 5 gigahertz, and then for the diagonal feed, the resonance was starting a little bit higher. And you can see the impedance is very high. This is because we have the coaxial feed placed at the edge of the antenna where the impedance is characteristically highest. So while this gives you an idea, once again, of where the antenna would resonate and how it would operate, this is not the antenna after doing impedance matching. And here we see that for the 104 and 36 degree rhombus, which is the narrower design, we have a different sort of radiation pattern. The energy instead is split again, the same way that it was for the diagonal feed for the wider rhombus. It means that the energy is being distributed evenly but not center, the way that it would ideally be for a patch antenna. However, we're still getting peak gains pretty similar to what would be expected of also regular patch antenna designs. So those rhombi were arranged into a design, and this is basically what we were studying. You can see the slots implemented into design. That serves as the sort of anchor points for how we can so those serves as the anchor points that we use for how to arrange the rhombi, because you can arrange a bunch of rhombi together, and that's not necessarily going to be a Penrose tiling arrangement. It has a sort of rules of play, and those were shown in an earlier image. But we essentially use the slots as a sort of anchor point, but para dejarnos llevar. I'm sorry, I don't know how to translate that. As a reference for how to continue arranging the sort of geometry of the patch. We simulated that from 0.5 to 4 gigahertz because I'm going to go back to the previous slide. We approximated this particular design of a Penrose tile to that of being 3 circular patch antennas, and we were able to calculate the resonance points where each of those circular patches should be, and based on those frequencies, the highest that we got was about 3.5 gigahertz. One was at about 1.5, and the other one was about 800 megahertz. So that's why we did our frequency sweep from about 0.5 to 4 gigahertz. And you can see the S11 here. What we were mentioning about broadband designs, you can see how there's sort of a bunch of loops happening around within the Smith chart S11 parameter. What we are trying to do is basically take those loops and bring them as close to the origin point in the Smith chart as we can. It's not necessarily going to be perfectly matched. However, if we can achieve a return loss between below negative 10 dB for a wide band, that would be ideal. That's what we're trying to achieve here. So the idea is to bring those loops as close to the center as possible, as consistently as possible. And here are the results for the gain simulations of the Penrose antennas. You can see again, for the first simulation, we placed the coaxial feed at the bottom of the design. And the gain, again, the energy was a little bit unevenly distributed, but we did have a peak gain that was a little higher than a patch antenna by about 2 dB. If it were 3 dB, it would be approximately double, so this is significantly higher than a regular patch antenna design. And on the right, you can see for the top coaxial feed position, it was a little bit more focused toward the angle theta equals 0 degree, which means directly perpendicular to the patch. So for our conclusion and future work, we basically successfully analyzed the rhombus designs and the provided Penrose patch antenna design. And the design does provide a better gain in bandwidth than conventional patch antennas, such as regular rectangular and patch antennas. And also, particularly the rhombi, this is another thing that we can include in future work, but it was showing pretty good circular polarization. So another thing that we can do is a study of the axial ratio of that antenna as we change the feed position. And another would be to use different parts of the Penrose tile geometrical arrangement and include it into the patch design to see how that would affect, again, gain, bandwidth, and return loss, so that we can have a good sort of scalable design for an antenna that could be implemented in microstrip and it'd be broadband and higher gain than regular designs. So are there any questions from the audience from YouTube?
Thank you.
Estoy dando eject. Ya está.
Our next group is UPRM Solar Boat 2025. There is a lot of names in this presentation, so I will read a few, but not all. Eduardo Lopez, Cristian Roman, and Carlos Santos, Sergio, etc. So, please.
Well, good morning, ladies and gentlemen. We are the UPRM Electric Boat Team, proudly representing the University of Puerto Rico at Maya West. My name is Ronald, and together with Abel Ortiz and Victor Herena, we will be telling you about our journey with our electric boat project. For several years, we've competed in a challenge called Solar Splash, a collegiate competition where teams must design and build electric-powered boats. It pushes us to innovate our design with the constrained rules they have. We have 100 pounds of energy storage that we can only limit ourselves to, and that battery pack may only be charged by solar panels. We are tested in 3 events: the sprint event, which is the fastest we can go, the endurance that tests how efficient our system is, and slalom that tests our maneuverability. These were last year's results. As you can see, we've earned first place in the sprint, a video presentation, and technical reports. And our rewards were in system design, drivetrain, and overall workmanship. And it was a proud testament. It was a proud moment for our team and a testament to the hard work we've put in pushing sustainable marine technology forward. This year, we're aiming even higher. We're participating in a Monaco Energy Boat Challenge, a world-class international competition focused on the future of clean marine propulsion. And here's the exciting part. We're actually the only team from the United States competing in this prestigious event. And our we have to design, oh, excuse me. Our objectives for this year are ambitious. We're actually engineering and manufacturing a custom cockpit, a new battery enclosure, and a redesigned transom, which all have to comply with the rules and technical regulations of the Monaco Energy Boat Challenge. And our biggest target this year is to increase our door speed for the Endurance event to a 4.3 meters, which is a 30% boost from our Solar Splash competition.
For our electrical objectives, we need to design an electric propulsion system using a motor, a controller, and data acquisition system. For our design, we chose 48-volt lithium-ion batteries, and our data acquisition system contains telemetry and CAN bus communication between components. For our electrical layout, we have two main systems. We have the high voltage system and the low voltage system. The high voltage system mainly contains the motor, the batteries, and the motor controller. Our low voltage system mainly contains the data logger, telemetry, the throttle, and deadman switch. For our high voltage system, we have 6 48-volt ion batteries in parallel connected directly to the controller and to the motor. We also have a 500 amp fuse just in case anything happens. For our low voltage system, we have a data logger that is the Race Capture Pro connected to our various sensors, and we also have a throttle that is connected to a controller via CAN bus. We also have a shutdown circuit because of the rules compliances just in case an emergency happens. For our battery selection, we dialed it down into two main options: a custom pack, which is the P42A, and a commercial option, which would be the GC2R brand. Our deciding factor on which we are going to be dialed it down into cost and ease of implementation. As you can see, these are very much more financially viable than the custom option.
Let's talk about the data acquisition system. We mainly collect three types of data: the analog, CAN bus, and GPS. Via the analog system, we get all our sensor data, which we implemented in our boat, which will be used to calibrate and improve all our system. Through the CAN bus, we actually capture all the electric consumption, which allows us to track performance and quickly diagnose any issues. And the GPS data is used to ensure the accuracy of our speed readings and help us validate our sensor data using real-time world tests. Our telemetry system is centered around a Raspberry Pi that is connected to a cellular network for real-time data streaming. Using custom data logger software, we upload performance data to our cloud server, enabling remote monitoring from internet-connected devices. Additionally, to meet with the conditions set by the Monaco Energy Boat Challenge, we must send through an API our battery temperatures.
The mechanical engineering team has been actively working on the design and manufacture of different components on the boat from the ground up. Over here we have the cockpit. The cockpit has a modular and aerodynamic design to help us minimize the air resistance, which will give us a better performance in the competition. It's going to be held down by U-bolts, which are going to be movable. And behind the cockpit, we have over here the dashboard. This was the main idea. The picture on the bottom is what we have right now. As you can see, it has a switch box. On the switch box is going to be included reverse gear, a switch for the reverse and forward gear, which the Solar Splash boat did not have. It's going to have a battery display to monitor our battery temperatures, which Solar Splash didn't have either. On the other side, that hole over there on the right is going to be the throttle placed, which is currently now being 3D printed. The drivetrain design over here, we designed a transom, which is the part that holds the motor. It's made out of wood and aluminum, coated with resin. We kept the same motor we used on the Solar Splash boat. The drivetrain, the only thing we changed, we extended the drivetrain by 7 inches. We're going to place the propeller about 3 inches below the water line, which we expect is going to have the best performance. And over here we have the holes. The picture you see on the left side is the hole design. The competition is going to provide us these holes. Keep in mind, these holes are in Monaco. Over here in Puerto Rico, we have to make our own holes to try out the boat. So the picture on the right is the hole we have already fabricated. We're last touches to go on and do the second one. Keep in mind, these holes are 16 feet each. This is basically the final design of the boat. As you can see, in the front part is going to be the cockpit. The middle part is going to be the batteries. And of course, on the back part is going to be the motor. Over here, we have the weight display. We have a maximum of 705 pounds. Right now, including the captain, we are at 660 pounds. So we have about 40 to 45 pounds to play with. These are our tasks, what we have completed: cockpit, hull, dashboard, and electrical design. We're working right now, of course, on finishing the vessel. Component optimization, that's once we have everything done. The speed goals, of course, we're gonna take a look at that once we finish the boat and we try it out in the water. We are trying to reach a 4.3 meters per second speed on the endurance and a 10.7 meters per second on the sprint competition. Of course, we're going to try to meet with the competition regulations, and our final objective is get to Monaco and participate in the Monaco Energy Boat Class competition. Thank you very much for your time. Any questions? Feel free. Yes, ma'am? Yes. Are the goals related to the competitors, other competitors in Monaco? Yes, yes. We actually, last year, members of our team went to the Monaco Challenge, and they studied all the competitors. They prepared a paper for us to review. We studied what their boat was like, what batteries they used, what design they had, and based on that, we worked out on our own design.
Yes, for the benefit of the audience on YouTube, please use the microphones for the next questions. Any other questions?
Anybody else?
Thank you very much.
Thank you.
Thank you.
Our next presentation is Protect Innovation, Design and Construction of a Robotic Hand with 3D Printer and Sensors. Our students are Nathanael Batista, Brian Vasquez, Marcos Perez, Cesar Espailillo, Kevin Gomez, Pablo Figueroa, Esteban Porcel, and Mia Fuentes. ¿Me lo enviaron? Dale open.
Hello, my name is Nathanael Batista. I'm here with Carla Rodriguez, Brian Vasquez, and Kevin Gomez, and we are on behalf of the team of Protest Innovation, and we will present our project about design and construction of robotic prostheses with ENG sensors. Our vision as a team is to design and develop an accessible functional arm that is controlled with the EMG signals and is able to replace the hand and forearm of our patients. We divided the whole process in 3 phases. The first one was the design of the prosthesis arm. We needed to check which electronic components were needed to function as a functional arm. And then, based on that, we designed the arm and we printed it with 3D printing. And then from the phase 2, we built the circuit with those electronic components. And then for the phase 3 was to unify all those phases and do a functional arm. So I will let you with my peer, Carla Rodriguez, to show you the design.
Thank you. So first, the design should be adapted to the arm structure and the body contour so that we don't cause any pressure points. In the image, we can see the 3 parts of the arm that we focused on, them being the joints, the tendons, and the fingers. The tendons will later on play a crucial part in the development of the prosthetic arm. The material should also be lightweight and compatible with the skin so that it is comfortable enough for the patient to wear. Here we have the first design that it has a flat structure, but it focuses on the hand opening and closing motions of the fingers. Here we can see that it is divided into 2 zones, zone 1 being with an elastic part that it helps close the fingers, and the zone 2 being the part that helps us open. Each finger is connected to an individual servomotor that is the one that helps with the movement and gesture of the closing and opening of the hand. And now I'll leave you with Brian Vasquez, sorry.
Moving on to the second phase of the project, here we have a flowchart that showcases the structure of the circuit. First, these signals are gathered through some electrodes that send the signals to an EMG sensor, which I will further explain in the next slides. This sensor amplifies and filters the signal, and then sends it to a microcontroller that interprets those signals and moves and actions the arm, generating the hand movement. Here we have our original circuit. The circuit was chosen because of the accessibility of the components. Here we used servo motors to actuate the closing and opening of the arm, an Arduino as the microcontroller, and the red PCB, as you can see there, is the EMG sensor. As I said, after the signals exit the electrodes and enter the amplifier, the EMG sensor, they are met with this first barrier, which is the instrumentation amplifier. This amplifier has what is called a high common mode rejection. That means that when 2 signals are equal, they cancel each other, but when they are different, the amplifier amplifies the difference. Usually, the signals that are equal are usually noise because one of the electrodes is usually connected to a bony area of the patient, and that usually has a lot of noise. And when the signal is different, yeah, it manages to amplify it and, well, continue. When, after it's amplified, it enters the filters, active filters. Here we have active high-pass filter and active low-pass filter. The active high-pass filter filters signals after a certain frequency, and the low-pass filter lets signal pass below a certain frequency. We use active filters because they function in the range of up to 0 hertz around, which is the range of the EMG signals. In addition, they have some gain that actually helps us process the signal. Afterwards, after the signals are amplified and filtered, they enter the final stage with the non-inverting amplifier that help us get that last amplification that we need to process the signals and send them to the microcontroller. As you can see here, we have a circuit. This is what is inside the red PCB I mentioned before. And as you can see, it does not have the amplification and filtering that I have mentioned. For that reason, our signal was not getting the proper we're not getting the proper signals. And for this reason, we made some changes to the circuit. The first change that we did was change the EMG sensor to the Biomp XPIL. This sensor contains all the amplification and filtration that I mentioned before. In addition, it only functions with 5 volts, and it's about the size of a coin. Another change that we made is we changed the servo motors to these DC motors that actually lower the area the motors covered in the hand, which is very important for us, ranging about 50 millimeters in size. In addition, they add more torque compared to the servo motors, having a ratio of 1,000 to 1. Another change was change the disposable electrodes to dry cell electrodes, because we noticed that after continuous use of these electrodes, they lost their functionality and thus hinder our data acquisition. To move the DC motors, we used this motor driver that we mainly chose this because of the size.
Another change we made was to change from a microcontroller like Arduino to a Raspberry Pi as a single board computer. Why is that? Because Raspberry Pi's computational capacity is able to run machine learning models without needing an external computer. So that allows us to predict the movement of the hand using the EMG signals and pass it through a machine learning model. And we can predict if the hand is open or closed based on that. And here we can see a testing of the DC motors. We have a video here where we are moving the DC motor here using the EMG signals. And then, why is machine learning important for a project? It's because to be able to predict more complex movements, we need to analyze more data, a vast amount of that. Like, not only from one part of the arm, but several points in the arm, meaning several sensors. Another improvement that machine learning has is that it can ignore noise and electrode shift, so it can ignore the non-necessary part of the signals. Like, it can not only, we can select which signals we need to predict the movement. And then, to get data, we use 4 test subjects from each group ranging from 19 to 21 to be able to not have bias in only one person, but to be able to predict in a more general manner. We did the testings using 2 simple movements, like closing and opening the hand. And then we collect the data using like 2 minutes of opening and closing the hand, and putting a status of 0 or 1. And based on that, we train our model.
Thank you. Okay, so he talked about machine learning models. Currently, we've been through 3. The first one was a multi-layered perceptron, multi-layered perceptron that used root mean squares training strategies. It's a very common training strategy for machine learning models. Basically, it takes a type of average from the errors that you have to make sure that you have the most smooth prediction. The second one that we did is a logistic regression model, which also is very common and showed similar results to the first one. Now, the last one that we did, which actually showed the most, let's say, smooth or accurate results, was the multi-layered perceptron using advanced momentum estimation. This basically means that during the training process of the machine learning model, the learning rate of the model is dynamic. So you can see the first image to your left is actually the one using the MOP atom. You can clearly see that's the one with the smoothest accuracy curve and the one that reaches that curve the quickest and stably. So what do we want to do to close that 10% gap? Because they all had 90% accuracy. Well, what we want to do is, as he said, increase our data volume. We want to grab more subjects, and we want to extend the training period of the model so it has more time to analyze a person's signals, understand what is being done by the hand. We also want to do advanced modeling with windowing, which effectively means separating the EMG signals into windows or slots so that we can analyze them by part and have the most accurate results every second and every moment that the patient does any movement. And we also want to upgrade to multi-channel sensors. This means not only opening and closing, but actuating every finger individually like you would on a real hand. And with that, we're also going to be doing some upgrades to our machine learning, let's call it architecture, but I'm going to talk about that in a few moments. Here you can see a demonstration of the readings with the EMG sensor. You can see that they're very noisy, but still we had very accurate results, which showed machine learning's capacity to smoothen out that noise and really make it more viable to understand. And here you can see the result of phase 2 and phase 1 during testing. It shows the hand is fully functional for opening and closing using the machine learning models. You can clearly see that is a very slow hand. This is because we opted for a faster architecture for development, but not necessarily a good one for deployment. But this is okay, this is part of our plan. We wanted to test as soon as possible and then move on to optimizations. One of those optimizations is using TensorFlow Lite for deployment. This means that the machine learning model will be a lot more efficient, especially on a microcontroller, as even though the Raspberry Pi is very powerful, it's still a very limited computer. So it can still work very well there. Something else that we want to do to ensure that everything works as fast as possible is employing the robotics operating system communication system. This basically is a way for everything to operate individually. You're going to have readings at the same time as DC actuation and machine learning processing. So that really helps to raise the quality of the product as a whole.
So to summarize our resource, we did the optimal design which accomplished our initial objective. That was only closing and opening the hand. And then we were able to read the signals of the EMG sensors. And with that, we trained our machine learning model. So that will be the resource that we have currently. Our next steps will be obtaining a sensor with multiple channels or using multiple single channel sensors, like my peer Kevin said. We need this to be able to to predict more complex movements, because we only use opening and closing hand because we only have one sensor. An EMG sensor is very hard to get, so we will be searching about a sensor that can meet the need. So for the calibrating DC motor, we need to use encoders to be able to move the DC motors in a more precise manner, to be able to not only move one finger without that much precision, but to be able to do it with using angles and more slow and fast manner, depending on what the patient wants. And to have a bigger database using those sensors, like I said before, we need more channels to be able to get the model to predict a more complex movement. So getting a bigger database using those sensors and with more people, because we did the testing only with young people ranging from 19 to 21. So we need different types of people with different physical condition and different variables that we can use to train the model to be able to train to predict in a more general public. And because we need to have a bigger database, we need to have better models of machine learning to be able to predict, to use that data effectively. Like, we need to change the models that we are using, because we only use that because we are using two movements. So in the case that we get to predict more complex movements, we need to change the structure that we are using. These are the references that we mainly use. And I want to give a special acknowledgement to the University of Puerto Rico, to IAP, to Minds to Create, and protects our whole team. Thank you very much.
Are there any questions regarding the software, mechanical, bioelectrical, anything? No? We're good. Thank you for your attention. No? Oh, sorry.
Just a quick question. I was wondering, where does this part attach to humans, or how do humans send information to how they want their hand to move, if that is part of your project?
I could take this one? Yeah, okay. So the prosthesis is meant to be attached to the part where people lose their limbs. So about here in the forearm, I believe, right? And you would move it as you would your other arm. Effectively, when you lose an arm, your brain still sends signals to that part of the body. So we measure those with the sensors that we talked about, and then you just use it as you would your other hand.
Yeah, we have a biology. We have a biology division with is searching to be able to not only have a 3D printed hand, but to be able to fuse it with the human body. Like not only the technical part with mechanical and software and electrical, but we have people with that knowledge in the team.
Since bio signals tend to be very, very low, what was the amplitude or the magnification that you needed to implement to be able to move the motors on this particular hand?
Well, we used like the amplifier that we're using. It's 1,000 volts by volts, and that's usually around that we need. Those signals are in the range of from almost microvolts to up to 10 millivolts, and while it's amplified, it ranges up to 1 volt or something around that range.
Thank you.
Are there anyone else with any questions? All right, then thank you for your attention.
Our next presentation is Advancing Power Electronics Education through Real-Time Simulation and Control and Grid-Tied and Grid-Forming Inverters for Undergraduate Training. Our students are Jose Moll, Edward Figueroa, Emanuel Ocasio, Marcos Rivera, and Gabriel Cedeño. PowerPoint, ponerlo con file open.
Sí. Okay, good morning everyone. My name is Gabriel Cedeño, and I, with my team members, we are going to talk about our research and training project focused on the simulation and control of grid-tied and grid-forming inverters. This is focused for students that are undergrad. My team members are myself, Gabriel Cedeño, Marcos Rivera, that is going to present with me, Edward Figueroa, and Emanuel Ocasio. So first, we're going to talk about the content of this presentation. First of all, we are going to present the motivation of the project, the research question, introduction. I'm going to talk about the DC-DC converter model and simulation, and Marcos is going to talk about the DC-AC inverter model and simulation. The experimental setup, the simulations, and what we do in the experiments in the lab, the experiment video, closing remarks, and your questions and answers. So the motivation of the project. So power electronics is essential nowadays because we can see it in every electronic devices. We can see it in laptops, renewable energy. We can see it in smart grids, and they play a critical role nowadays. So, like education nowadays, they tell you more theory, and they give students little exposure to real-time systems and invert control, which are essential in the job. And here, it where this project comes. We use tools as Opal RT, PE Lab, that enables safe, cost-effective experimentation with complex grid scenarios, and this project fosters critical thinking, system-level understanding, and industry-relevant skills through experiment learning. So the research question. In DC-DC converters, we use the boost converter and the CEPIC. So the first question was, how does varying duty cycle affects output voltage and efficiency under different load conditions? What are the dynamic response, rise time, settling time, that's the control part, of boost versus CEPIC and converters during line load transients? In the DC-AC part, how do different PWM techniques, unipolar versus bipolar, influence inverter output, harmonic, and THD? What is the role of synchronization in stable grid connection to single-phase inverters, and how does real-time simulations assist in evaluating anti-ice landing protection strategies? So this is our project overview. So we use Chroma as a source to be connected with the PE lab. Inside the PE lab are the converters and the inverters. We made the connections in the lab, and the RCB is capable of controlling and configuring the PE lab. The PE lab too, we can see, if we connect the computer, we can see the results and the data in the PE lab. So what are DC-DC converters? DC-DC converters are electronic devices that they convert a DC input to a different DC output, and it can be higher or lower. It depends in the type of converter that you are using. We can see applications in, I already said, in every electronic. We live in an electrical world, and types of converters, of DC-DC converters, can be buck converters, boost converters, buck boost converters, and CEPIC converters. In the left side, we can see the boost converter that his job is to convert a lower DC to a higher DC output voltage, DC value. The buck boost, it can both increase or decrease the output, the input, sorry. And in the output, you get a reverse polarity. So if the input is positive, well, the output will be negative. In the CEPIC converter, functions the same as the buck boost, but in the CEPIC, we have the same polarity as the input in the output. So in the first simulation, in the left side, we see a PV source connected to the boost converter, and the load you can see that it's in the middle. And in the right side, you can see a battery connected with the buck boost bidirectionally. So to explain it more graphically, when the irradiation is 0, you can see in the down in the right that the battery, that's the current battery, the battery is supplying the load. You can see in this graph too that when it gets to 800, when it gets to 800, the battery starts to charge in the left down side. So we want to, in the middle right, we see the VV. We see that that's the voltage DC. Sorry. Okay. Thank you, Emanuel. So you can see here that this is the VV, is the voltage DC of the battery. And while we are increasing time, we can see that the battery, when it hits here, when it hits zeros, it starts to charge in 1 second. It starts to charge. And the voltage, like we want to balance this voltage. So it increases the irradiance, but it stays the same, thanks to the battery. This is the CEPIC. The second simulation is the PV. With CEPIC and battery with bidirectional buck boost, we can see in this part that this is the PV source. It's connected to the CEPIC converter, to the load, and the battery is connected to the buck boost. And we can see here the same behavior, but when the irradiance increases to 400, we can see the difference between the behavior of the V bus, the voltage bus. Here we can see a difference. And now I explained the DC-DC part. I'm going to pass Marcos the DC-AC part. So, come Marcos.
Thank you, Gabriel. Now we are going to focus on the DC-AC converters that we analyze and simulate for this project. But first, let me give a very brief explanation of what is an inverter. An inverter is an electronic device that converts DC current to AC current. It can be that DC current can come from a battery or a renewable energy such as a photovoltaic system or any other type of source. For this project, we simulate for 2 types of inverters: single-phase inverters and multi-level inverters. Can you take that one? Lisa. Okay. So for the first simulation of single-phase inverter, we use a pulse width modulation of unipolar. As you can see, the output waveform of the single-phase inverter using unipolar, it is like a smooth waveform. So we can observe that there is small harmonic distortions, and proving that the unipolar pulse width modulation is great for for producing minimal effects on the waveform. So for the second simulation on the single phase inverter, we used a different pulse width modulation that is called bipolar. As you can see in the control model of bipolar, you can see that it is more simpler than the unipolar control model. But the waveform that produces in the output shows that there is a lot of harmonic distortions, so that is bad for the waveform. Now I'm going to proceed with the other type of inverter that we simulate and analyze. This is the H-bridge cascade 7-level inverter, which consists of 3 inverters interconnected in series. So for these simulations of multi-level inverters, we use only unipolar pulse width modulation. As you can see, this is the output waveform. It has 7 levels of voltage. Now for the second simulation, we use a H-bridge cascade 13-level inverter with the same pulse width modulation, unipolar. As you can see in the circuit, we have 6 inverters interconnect in series. You can observe here in the output of the waveform, in comparison with the previous simulation, that the waveform improved its quality and reduce the harmonic distortions because of the increase on level on the inverter. So now I'm going to explain the experimental setup. It consists of a photovoltaic system connected to a DC to DC converter, connected to a DC-AC inverter, and finally connected to a load. So for the emulation of the photovoltaic system, we use chroma. And for the simulation of the DC converter and the DC-AC converter and the load, we use the PE lab, programmable converter and inverter. We use this device here as the rapid control prototyping to configure the PE lab with the DC to DC, DC-AC, and the load. Here we have the results of the experiment. This is the DC link voltage that gives us a 36 volts. And this is the 3-phase current, 11.5 amperes per phase. This is a picture taken of the intelligence analysis, the data acquisition of the experiment. So now I'm going to pass to my partner Emmanuel, that he is going to show an experimental video and explain it.
Thank you, Marcos. All right. As you can see here, my partner Gabriel is short-circuiting what is the PE lab. If you see, the green cable represents the connection through the chroma that Marcos was explaining, and the black cables, when the chroma is connected to the PE lab, it goes through the DC to DC, then to the DC to AC, and that black cable that was connected on the left, like Gabriel was connecting, like next to that cable to the input, he was connecting 3 cables, that was to short circuit those inductors, because inside of that PE lab there's inductors, and that's going to be our load. And now we're connecting the PE lab to the computer, and now we are, let me go back. Okay. Gabriel is short circuiting the load inductors. Connecting it to the computer, using Chroma to set the optimal voltage, short circuit current. We turn on the PE lab, and we get results in the computer. Then we proceed to change frequency to see the response of our system. There we go. Thank you. Now I'm gonna leave Marcos with the closing remarks.
So for our closing remarks, well, this project gives students hands-on experience, while you know that in the majority of the classes, we only focuses on the theoretical concepts of the courses and all that stuff, but this project gives students the opportunity to have that practical experience that in class we don't have. So we, like Emmanuel said, we work with tools like Chroma, PLab, and the RCP controller that we, obviously in class we don't have that dynamic of understanding how to work with the power system and power electronics situations. And this project not only deepened our technical skills, but also prepared us for the real world challenges that we have now in the electrical grid. So we thank UPRM and the IAP program for promoting innovation and active learning in undergraduate and graduate engineering education. So we have 2 papers accepted on the Frontier in Education. So yeah, thank you for your attention. Any question?
One quick question. Your simulator is for both grid tight and grid forming.
Yeah.
So for grid forming, what is the capability for you to? You need at least 2. And how many can you simulate? Up to which number?
Okay, so now we just we only analyze the converters and the DC AC inverters, but we still are working a load. Like in this experiment, the load was the inductors that were in the PE lab, but we are not next semester we are going to still working with grid tight and grid forming inverters.
Any more questions? Thank you. Our next presentation is the MacroMouse robotic project The students are Ordep Agustin, Andrea Gomez, Miguel Alejandro González, Luis Luna, and Brian Figueroa.
All right, test. All right, sounds good. Good morning, my name is Ordep Agustin. I'm the project manager for the Micromouse Robotics project. I'm accompanied here by Brian Figueroa, one of the team members. Luis Luna couldn't attend today. He's currently in a co-op experience, and then the master students were busy doing their thesis and stuff, so they couldn't be here either. Our professor is Dr. Eduardo Ortiz. He is a professor here. He also competed in Micromouse during his competing days, and he was the advisor for our project. So I'll leave you with Brian for the overview.
So, a quick summary of what we're going to talk about today. So we're going to talk about what is Micromouse, the purpose of what we do in Micromouse, our niche and design, the competition, the PCB prototype, and future plans. So what is Micromouse? Micromouse is a small autonomous robot equipped with various sensors, hardware, and algorithms designed to navigate and solve a maze as quickly as possible. It serves a platform for exploring real-world application of robotics control systems, algorithm optimization in competitive settings. So what we are doing, Micromouse, it demonstrates advanced engineering skill by developing a fully autonomous robot capable of efficiently navigating and solving a maze as fast as possible. Integrate sensors, control systems, pathfinding algorithms to push the limits of robotics and embedded systems design, and to compete in the IEEE Applied Power Electronics Conference Micromouse competition. So, when we started this whole project, we started with a design of our own Micromouse, and we have a bunch of algorithms that we're going to talk about later on the presentation. And we researched all these algorithms, try to optimize them, and research the materials like infrared sensors, microcontrollers, and other materials. We started with a design of a PCB, and then, because we didn't know a lot about how to construct this Micromouse, we decided to use a learning with starter kit of a Micromouse and a test pre-built starter kit to test our algorithms.
Thank you, Brian. To get started with the starter kit, like I mentioned, it is a starter kit, so this is open source. I credited the author there. That is the PCB design that he has for the kit. As you can see, it uses a lot of sensors, a lot of infrared capacitors to help with the load. I'll show a different picture of the fully built mouse as well. I do want to preface in the bottom right, you can see a little box where it says function. That one is where we activate to search the maze, solve the maze, optimize, speed it up, stuff like that. And it uses two 650 batteries. So here is our pre-built starter kit. This picture is also from the website that we purchased it from. As you can see, it labeled all the different components that it uses. It's using specifically Arduino Mega Nano and a N20 gear motor. I focused those two because those were two bottlenecks that we encountered during the competition. And as you can see, this is the story of Pedro. Pedro is the name that we gave for the Micromouse. We used it to try and... Fun fact, it's Pedro because it's my name backwards, and they wanted to make it a joke on me. So there you go. A little bit more of why we chose this model. It was open source. It was based on one of the competing winning models as well. It's from the UK MarsBot team, and we basically use this model to solve our makeshift maze and test our algorithms to see if it was working. Speaking of those, the two algorithms that we mostly studied and used was the A-star algorithm, which is basically a pathfinding algorithm that uses different nodes and assigns values to them, and you can just find it with a weighted graph. And we also use the flood fill technique, which identifies and alters a connected area with a multi-dimensional array, as you can see with the picture to the right in this case. That is the algorithm that Pedro is mainly using. I highlighted in 4 little red circles those numbers. Each number represents how many moves it takes to reach the center of the maze. To keep the competition a little consistent, they define where the start gate is, but prior to the competition, and everyone bases their algorithm from that start position. The center is usually always in the center as well, but the path to get to it is what changes every year. They have a dedicated person who designs the maze, and they are not allowed to compete in the competition because they know how to solve the maze beforehand. And a little thing I'm going to highlight as well from this algorithm. Here I have the empty maze data and the recorded maze data. The empty maze data, as you can see, it starts from 14, 13, 12, 11, et cetera, et cetera. That's just basically how many cells it needs to traverse to get to the center of the maze. The maze is a 16 by 16 grid maze. I'll explain that a little bit more in the competition section. And when we look at the recorded maze data, as you can see, we have a lot of 255s, 240s, stuff like that. That was one of our bottlenecks. Our microcontroller was actually running out of memory to reach to the maze data with all the movements. We later found out that the sensor data was being filtered incorrectly, and I had to fix that on the spot during the competition. It used the data from the infrared sensors to calculate if the wall was to the right, center, or left, and it would just record the walls based on that algorithm. And the main problem was it uses an A to C converter, and the channels were switched from the original model. So you were detecting your front on your right side, your left on your right, and your front on the left. It was a whole mess. So even with all of these challenges, we still went to the competition. This competition took place in March, say 16th, 17th, around that date. As you can see there, I'm proudly holding Pedro. He is very tiny. He is in my hand. And like I mentioned, it's a 16 by 16 grid maze. Each grid measures 18 centimeters by 18 centimeters, and it's held at the International IEEE APEC Conference. Competition was tough because we're not competing against students. We're competing against full-time engineers who have been doing the craft for many, many years. Some legends that I like to highlight is Peter Harrison, Yuta Takamoto, and David Owen. They were like, I have a picture with all of them. I just picked one I'll show later. And as you can see at the bottom, Pedro has his own little certificate as well for competing in the maze. And over here, I have some other competitors as well. The gentleman with the trophy with a very small mouse, that is actually a half-size mouse. He competed the full maze with a half size. To give a little bit more context, the competition is divided in a full-scale mouse, which is the 18 by 18, and then half size is 9 by 9 centimeters. And he said, you know what, I'm going to compete in the full scale with a half scale, and he actually got, I believe it was 3rd or 2nd place in the competition. Next to him are 2 of his students who he has been training. They're all from Japan, and then next to him is me in the middle, and to my right as well is 2 other students, one from California, one from Michigan. We connected, and I have a lot of information. We've been sharing ideas for our next models, stuff like that. And I unfortunately cut his head out, but the man with the nice power stance is Peter Harrison. He's the one who actually won the competition this year with his own model, and there I have a picture of all the models that were competing. It was a total of 16 mice, if I'm not mistaken. There were some last-minute entries as well, and they allowed them to compete. And yeah, it was a great learning experience. Some challenges that we encountered, which I'll talk about here in our future plans section. Basically, using the pre-built kit to test everything helps, but since that pre-built kit had its own errors, a lot of our decision-making, the algorithm was just flawed because of it. Like I mentioned, the sensor data being fed incorrectly, that is something that we found out a little too late to make the corrections, and as well as lack of experience in our own team of how do we make our own PCB, how do we make all these type of things. So for our future plans, we do want to have our own PCB design. We want to better our sensor reading. We want to have accurate maze detection and the flood fill algorithm to complete it as well. And we want to complete the maze with minimal errors. We don't want to be the fastest because competition is really tough and we're in the big boy leagues. But ultimately, we do want to compete in the APEC Micro Mouse Competition 2026. And yeah, basically that is everything that we've achieved. And that is all that I have to present for you guys. Thank you for your attention. I also want to thank our sponsors for the IAP program, and we'll open the floor for any questions. All right, thank you.
It's already 12 o'clock. I've been notified that lunch is already served. So let's take 1 hour of break. Let's be back at 1 o'clock sharp here. The lunch will be in the Tarzan room. All of you are welcome.
¿Quieres con portada? Sí, con portada mejor, ¿verdad? Sí, con la portada.
Good afternoon to everybody. We are waiting for the setup of the YouTube channel. So as soon as I get the signal, I will start. Alfredo, are we ready? Okay. So welcome to the IAP, the afternoon session. Our next presentation is Gravity Exploration through Visualization of Time-Space Deformation. The student is Pablo Portalatin.
Good afternoon. My name is Pablo Portalatin Ramos. My research is on gravity explanation through visualization of space-time deformation. Firstly, to start identifying what would be the concept of gravity and time-space deformation, we have to go to the fundamental basics of how Newton stated the three laws of motions. All three laws work to make what would be the concept of gravity. That is a relatively highly advanced, yet everyday phenomena. The first law of motion is the law of inertia. It states that an object remains at rest or in uniform motion unless acted upon by an unbalanced external force. The second law of motion, the second law will be the law of acceleration. States that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. And finally, the third law is the action of its action and reaction, stating that for every action, there is an equal and opposite reaction. With those three laws, we can start to formulate what gravity is. For Newton, the concept of gravity states that two objects with mass m1 and m2 with a distance r between its center are attracted with a force F. Below is the formula. This would be the formula of gravity, and the g's would be gravitational constant. I have a visual representation of how those laws would look. If we see two objects that are of equal mass are placed far, they will not attract each other. But if we move the objects a little bit closer, we can see how slowly one object closes to another. When we start to look at a video, when we increase the center mass, gravity, we see how it slowly starts pulling the farther mass object, stating that the mass higher has a higher gravity, stating that the farther object is gonna get closer pulled together. The essence of understanding what gravity is, if we look at the visual representation, would be this deformation that is slowly gathering. That would be how space and time is bending and how that attracts objects. As an object gets heavier and heavier, the mass gets denser and objects get pulled towards it. On these two simulations, we can see a comparison of a small object and a bigger object having an ellipse loop around a center mass. This is representing what would be the basic concept of an orbital loop across what would be our solar system. As we see, a smaller object gains a little bit more speed and has a more circular loop around the center mass. When we start to see the bigger object, it does have a little bit of speed, but it slowly starts getting to the center a lot quicker than the smaller object. This research was divided into two equal parts. It was a visual code tracking part and a physical model. I did a preliminary part prototype model that was trying to make a sphere that would rotate using the components of a plastic sphere, a switch, a 3-volt DC motor, and 2 AA batteries. This would be the prototype of how it looked, and if you look closely at the third image on the bottom part would be where the motor would stick out, and that would rotate, and when placed on the floor, it would do the rotation. For the visual tracking part, a Python code was done on OpenCV. That code, I'm going to show it a little bit. I'm going to show the key elements of the code. The code is supposed to track the object and keep tracking it throughout the duration of the elements. I'm going to skip to the video to show. The main objective was to track the center mass that would be the representation of what the sun would be, and orbiting parts that would simulate planets. As you can see, it does track the center mass that will be the one placed in the middle. The other parts that are orbiting are the planets. This part of the code was very hard to do in the specific aspect that a lot of elements could inflict. When doing the preliminary simulations, there was used the, I'm gonna go back a little bit to show, we used the metal spheres, the metal spheres, I don't know why it's not running right now. The metal spheres do reflect light, and reflecting light makes the system trick it with the light concept and not targeting, making a false positive mark that was not necessarily on the mark. It could be a little bit on the bottom or to the sides. To eliminate that problem, I decided to implement a white sphere. Any color would do, as long as it does not reflect. And to eliminate the shadow that would the object project, used a black background. That way, the image could be detected more clearly. The other problem would be that even though those changes were made, a false positive could occur in some areas. Specifically speaking, it's supposed to track everything that is within this circle, but sometimes it could give a false positive on the right corner or on the left corner, or even though could give a false positive on the center. That way, to make that part so that part did not happen, what you would do was, in the code, the parameters where you would detect the sphere, you would have to put a range on the distance from farther to closer. That way, it would detect the circle specifically where it is. That problem arose on the specific part when it was rotating, specifically more for the top area, because it's farther from the camera point than the one that is on the bottom that would be closer from the camera's perspective. Like I talked about, the light reflection was one of the problems occurred. The background color had a huge impact on the testing and the false positives that were detected. On the physical model, the sphere, there were a few problems that arose. Specifically speaking, when we are looking at the rotation that the object has, there has a lot of friction. The friction causes that the system has a lot of energy loss. That energy loss inflicts a lot of decrease in speed, and that is a huge point when wanting to have an object that rotates and it keeps being stable. For that aspect, two theories were done: either make the surface a little bit light, making the surface less, making it a point instead of being an actual surface when watching the sphere. Let me point quickly. Instead of using a sphere completely that has all the surface, making it just a point, making it balanced so that when it rotates, the surface is lower, thus the friction is lower. Or making the system move faster, that way it could compensate for that loss on speed. The other point that was gonna be implemented, but due to lack of materials, we couldn't, was make it so that the whole system would move, would be making that when the spheres are moving, the ring would move with it to compensate with the loss of speed and energy. In conclusion, I saw various fixes, various bugs with the code and fixed it. Although the code is ended, it could be optimized to make it a little bit better to detect more fluently, making the tracking more, make it track more per second, or the range of the distance to be tracked. The elimination of the reflection of the sphere was a huge change. was a huge plus. The background change helped a lot. And I talked about the hypothesis. Specifically speaking, what I like about this research is that I, as an engineer, am applying two types of concept, trying to visualize how gravity works in a scientific perspective, as also applying the engineering aspect, visualizing how it works differently and trying to apply a model that implements a closed loop system, that will be the sphere, and an image tracking aspect, that will be the code in OpenCV. That will be all for now. Thank you all from IAP and Professor Raul for this opportunity. Is there any questions?
Yeah, Pablo Portalatin, he graduates now in May, in a couple of weeks. But we have more development in this project. Can you explain future works, or how you close the loop, or what to expect if you want to use the vision part to create perpetual motion or something like that?
For the future would be one of the idea implementations that if it could be implemented, would be the compensation for the energy loss using some motors connected to the loop part of the system. If I can go back a bit, it will be using a ring basically with the spandex and putting the motors below so that it could move, and when the object is getting closer to that area, recompensating for that energy loss so that the system would keep its somewhat perpetual movement without affecting the system, because the sphere is not being tampered with. It's just the whole system, as to describe.
So any other question? Thank you very much.
Ya lo cerré sin querer. No, fue sin querer.
Our next presentation is verification of automated power system profile generation and characterization using a power amplifier. The students are Ricardo Garcia and Valentina Ramirez.
Hello, my name is Valentina Ramirez, and I am joined by Ricardo Garcia, and today we will be talking about automated power supply profile generation using a power amplifier. So the motivation for this project is to save time for characterization tests of a power amplifier by creating an arbitrary wave GUI. So our objectives were to create a GUI to program a function generator for any arbitrary waveform. Also, be able to create characterization tests using NI LabVIEW. Also, develop test stand sequence to be able to automate these tests. And finally, design a PCB for characterization testing on an actual op-amp.
So, as you can see here,
we have our arbitrary waveform GUI, and we can see that we have multiple waveforms concatenated with each other. We are able to create waveforms. We are able to also load waveforms, and if you already have a waveform, you can create a new waveform and append it to that previous waveform that you had. We have up to 8 different waveforms, either sine, sawtooth, pulse, square, and also you can concatenate up to 8 different waveforms. In the right part, we have the power supply configurations. Here we have how the oscilloscope part looks like. And if you press the stop button, we can see the full waveform in a static version. For the op-amp selection, we had a minimum requirement needed. So we needed to be able to handle this load, the slew rate, and a minimum calculated current for the slew rate was 25 milliamps. So we as a team chose the OPA 551 that meet with this criteria. For the methodology, we did a literature review. We determined the specs of the power op-amps. We developed a GUI for common tests used for characterization, such as continuity test, leakage test, and slew rate. And we aligned this test in the test stand and obtain a report. Right here, we have the continuity test that it takes up to 16 pins. We can set it up. It depends on your DUT. It injects current to look at the voltage drop on the ESD diode. And here, we see the leakage test. In the leakage test, we inject a high voltage or a low voltage, a high voltage and a low voltage to see the current leakage. This test depends on the DUT that you're using, and you gotta look at the data sheet of the DUT to set it up. For the slew rate test, this is the progress that we have. It is still in progress, but we can customize the waveform that we're going to input the DUT. You gotta configure the DC power supply, and then the output would be on the oscilloscope, and then it will be measured for the slew rate.
So here is our test stand sequence. So test stand is a software that lets us automate tests, and it's directly compatible with LabVIEW. So this is the sequence for the continuity test specifically, where the parameters for the LabVIEW GUI are preset. And then the user can set the pin to be tested, and then once the test is done, a pop-up will appear that lets you know if the sequence passed or not. So similarly to the continuity test, this is the one for leakage, which you can also preset all of the parameters for the LabVIEW GUI, and then the user gets to decide the pin to be tested. One of the advantages of using test stand is that it creates a report, and it lets you know if the tests passed or not and how much time it took to execute them. So this is the PCB board design that was designed, but it has not arrived yet. It is now in manufacturing. So on the design, we separately made each test in a different setup, preliminary, and for connectors, we used SMAs to be able to input our SMUs and also function generator. And since each test has a different setup, there is going to be a different socket for each test. Here is the PCB board, the 3D view. You can see all of the sockets for each test. For the DUT, also all of the input and output connectors. So a big problem with this is that we want to optimize the time of testing. So it is not the best to have different sockets for each test, because the engineer has to manually put the op-amp into each different socket. So to be able to optimize it into just the use of one socket, we were going to add a counter and a demux to be able to switch between all of the pins of the DUT, and then be able to do all of the tests in one single socket, thus eliminating the use of separate sockets.
As for the limitations that we have right now is that the PXI has up to 5 different modules. Our power supply can go to a maximum and a minimum value of plus and minus 20 volts. Our oscilloscope module, the resolution goes up to 125 megahertz, and the function generator right now
maximum frequency is 20 megahertz. We also have a limited amount of modules in our research lab.
So for the things we were able to accomplish up till now with our research is the VI to generate and read waveforms through the oscilloscope, also design the tests for continuity and leakage, also then develop the testing sequence for automation using test stand, and finally the design of the PCB to be able to do the test sequence on our op-amps. So in process, we have the manufacturing of the PCB, also the continuation of our slew rate test, and finally be able to actually automate the test with the PCB board once it arrives. So for future works, we want to increase the amount of characterization tests done. Since we only have 3, there's a lot more that we can do and automize, and also make a sequence for all of those tests in test end to be able to run them in order in one go on the op-amp. Thank you so much for your attention. I want to thank IAP and also our professor Gladys Ducodray for all of the guidance during this project. Thank you so much, and please feel free to ask any questions.
Yes. Go ahead. Stand to the microphone, please.
Hello. Is there a way to use this system in high frequency, for example? Maybe 10, 20, 30 gigahertz?
Right now we are limited with our hardware, but we are now measuring in low frequency. We can expand this actually to then make it up to high frequency.
Yeah, it all depends on the modules and the hardware that you have, but it is definitely transferable. And also with our PCB design, it would have to then be changed to be able to fit high frequency uses.
All right, thank you.
Thanks.
Yes, in power supply, you have two characteristics you need to check. One is the signal, which is the form that you show, and the other is the energy. So how much energy, how much watts you are supplying, or are you able to supply?
Right now, our power supply can go up to a maximum of 20. The component that we have right now can take...
The volts. You mentioned that you have to plus or minus 20 volts, but the power is in watts. So I need a current. How much current can I extract without losing the voltage?
Yes. So it is not something that we still have, I don't have the data for the current to be able to give you how many watts is able to supply, but it is something that could be found in the module's data sheet to be able to let you know. But at least for our use in a high power op-amp, it is able to supply the current. Thank you.
Any other question? You can ask. Yeah, sure.
Gladys is going to love me with this question, but I've been telling her that this is a very good project for Python environment. And just speaking from it, right, I actually can talk about many engineers that do not know how to use LabVIEW from start to end, right? Can you talk about maybe future work for this project, something that we can leverage in any other language, right? I want to keep it open, right?
So the advantage that we have if we can actually translate all this to Python if it was needed. Right now we were doing LabVIEW because it's a more friendly version since it's a block diagram that you connect one box with another. But we can fully pass this to Python if needed.
Yeah, I also wanted to add that National Instruments, and specifically, it has libraries in Python in which you can also control all of the modules, turn on and off SMUs. So yeah, it's definitely transferable.
And the great thing about this is that all the sequences that we have are not going to be lost because they could run in Python scripts too.
Thank you, guys. We need to find more students, right, for that?
I wanted to say thank you for all the questions and thank you for hearing us out.
Okay, our next presentation is Autonomous Underwater Vehicle for the RoboSoft competition of summer. I don't see the students here. Oh, that's why I don't see the student yet, okay? Okay, so I'm sorry about that. The next presentation is the RF low noise amplifiers and filter design using high electromobility transistor to reduce cooling power consumption. The students are Alejandro Martinez and Jonathan Rivera.
Where's the pen? Wait, do you have the thing? Here you go. This is supposed to be displayed for.
Is it not reading it? No, this is it.
Okay.
PowerPoint, I'm listening.
Perfect, thanks a lot. Other side.
Other side? Other side. Yeah. Where am I?
Yeah, right there.
Here?
Yeah, perfect. You can take control of the pointer for now.
Okay. Are we ready? Good afternoon. My name is Alejandro Martinez, and I'm accompanied by Jonathan Rivera. And I'm here today to present to you our RF low noise amplifiers and filter design using high electromobility transistors to reduce power consumption. Okay. So we're going to begin with an outline of what our presentation. So we're going to start with a system overview. Then we're going to go on to a focus and why. I'm going to explain to you why we're doing this project. Then we're going to move on to our spurious noise filtering system, then our amplifier system. And after that, we're going to explain to you some super transistors that can be used to improve these two systems. And then some future works, and then we'll move on to the summary. So with the system overview, we begin our story with our data collection, where we have an RF antenna collecting data ranging from the microvolts to the millivolts. And this could range from telecommunication signals or signals from space, which is what we want to work with. We send that data onto our analog front end, which is our part of the project. We are going to take that data and we are going to be amplifying those signals so that it could be later processed by our digital backend, which is in the signal processing block you see there. The digital backend is going to take that analog signal and convert it into digital signals, which will then be sent to the product generation, which is going to compile that data and change it into temperature, where it will be sent to our applications, where the astronomers can do what they want with that data that's collected. So our focus right now can be focused into two sections, our filtering section and our amplification. So in our signal filtering, we have a amplitude filter, which is going to take the data, which is going to be inputted our data, and any signal source that's going to be surpassing a predetermined threshold will be attenuated, and that attenuation is going to save our system from potential saturation, and which will lead to data loss. So in our amplification system, we're going to have a low noise amplifier. We are using a low noise amplifier as we want to be inputting and amplifying signals with as low noise as possible, as this is our first stage of amplification. Any noise that is inputted at the amplified in the first stage of amplification will be further amplified, which is which can later obscure our data, whether, it will obscure our data so that we can't tell our applications, or the data will be obscured between noise and actual data we want to work with. So why are we working on this project? So currently our system is working at a range of 4 to 15 Kelvin. We reached that temperature using liquid helium, which costs $48 per liter. With our new system, we should be able to increase that operating temperature to be able to work with liquid nitrogen, which will decrease that cost per liter by up to 99%. We are going to obtain this outcome with the use of gallium arsenide transistors, where we are currently using silicon transistors. We're going to be using gallium arsenide or even indium phosphide, as they have a higher frequency range, and they have lower noise at higher frequencies. Here we have some of our one proposed filtering system, amplitude filtering system, which is in the form of a winner-takes-all rank order filter, or the water off, which is used, which will take the input and can be programmed to either follow the maximum, the minimum, or the nth rank signal. This is programmed via a current source that, as you can see right over here. And any signal that passes our, as we are currently more focused on the minimum signal, as we want to work with signals from space, we are more focused with the minimum. So as you can see here, we have an example right here, and we're going to explain it further. But this data, as you can see, as the signal tries to surpass our predetermined threshold, it is completely attenuated, and this will lead to our avoidance or of saturation. So here we have our second proposed solution to spurious noise or saturation, system saturation, in the form of an active voltage limiter. So in this voltage limiter, we are taking the input data, which is going to be crossing through this resistor right here. And if it passes the threshold of this, which is given by this bias, right now we are working with 45 millivolts. So anything that passes 45 millivolts will activate this transistor, this N transistor, which will activate the voltage limiter. That voltage limiter will then attenuate the signal to below 45 millivolts. This will include some passive noise due to the resistor right over here. But if we keep the resistance at a low, and the ratio between this resistor and this transistor, which is acting as a resistor, the noise that is produced should be low enough to be still worked with. As you can see here, our signal is trying to surpass our 0.1, but the output signal is attenuated, so that doesn't pass as much as it's trying to. Here we have our low noise amplifier. The objectives of our low noise amplifier are to have a gain of 18 dB, of greater than 18 dB, an operating frequency of 1 gigahertz to 2.5 gigahertz, and more importantly, a noise figure that is below 1 dB. We are going to be achieving this with an LNA with an inductive degeneration. So now I'm going to pass it on to Jonathan, who is going to explain to you our super transistors and how they can improve our system's performance.
So the design of the super transistor is such that we want to grab multiple transistors and make them act as a system of a single transistor. So it's like working with more than one person in a team, assuming they're willing to cooperate, right? We have to have coherence with one another in order to get things going. Super transistors take the idea by grabbing two transistors, connecting them at their source terminals, and adding this transistor in the middle to provide a feed-forward path to boost that signal. We currently have 3 super transistor designs under the works, where we have a simple biasing current mirror for the super transistors here. Then we have a current mirror utilizing an op-amp for the super transistors. And finally, the third super transistor design is simply an operational transconductance amplifier, followed by a composite transistor stage. To evaluate these topologies, first we wanted to perform a literary review to see what available topologies are in literature. Then we want to design using Cadence Virtuoso, utilizing the UMS 0.18 micrometer silicon technology for our spurious noise filtering options, and then our super transistors. We then move to ADS for the low noise amplifier, utilizing gallium arsenide, same manufacturer. However, we have different sizes here because we wanted to initially send the layout for fabrication as quickly as possible, but they kept changing the date on us, so we had to act quickly and design with different sizes. Then we want to simulate all of the proposed devices before being able to integrate the super transistors with each of the devices. And then finally, we want to compare the performance between the single transistor variants and the super transistor variants. As for the rank order filter, we have the implementation of the super transistors here at the inputs, where we have two inputs, one of which is used to program the threshold of our filter, and then one processes the incoming signal. And finally, we have a diode-connected transistor, which is just a way of following the output signal. So for our current graph, we see that as soon that we program the threshold voltage at around 950 millivolts, as soon as the incoming signal shown here tries to exceed that threshold voltage, it is immediately excised, reducing the probability of system saturation. Then we have the case of the maximum. The previous case was the minimum. The case for the maximum, now it doesn't go below that threshold voltage. However, for our case, we see that there is some offset that is known as the edge error of our system. This is primarily due to the current mirrors that are biasing the super transistor up top, so it can't quite pull it down to the voltage that we want to. But that can be fixed with further system iterations. Then we have the low noise amplifier with the current layout. Utilizing spiral inductors, we use the scattering parameters, or S parameters, to measure our low noise amplifier performance, where our main focus was the S21 parameters, giving us around 23.5 dB, which is 5.5 dB higher than our original spec of 18 dB. As for our noise figure at room temperature, the reason why we did this at room temperature is because the current process development kit that we were using did not allow us to perform temperature sweep, so there was a limitation there. We had to design it based on room temperature. Now, for the ideal simulation, this is before the layout, we achieved the noise figure of around 0.15 at 2.5 gigahertz. And then as we performed the electromagnetic simulation with the current layout shown, we were able to achieve a noise figure of 1.58. So this means if we were to have been able to perform a temperature sweep and decrease the temperature, we would have been able to perform a better noise figure below 1 dB. Then for the super transistor test benches, we used two of the most common analog blocks found in analog system design, where we have the differential pairs, the single transistor variant and the super transistor variant, followed by the current mirrors, the single transistors here, and the super transistor implementation on the right. For the super transistor utilized as a differential pair, we can appreciate the DC transfer curve as we change the input, where the super transistors in cyan, gray, and magenta showed the greatest amount of change compared to the single transistor variant in black. We could definitely show the rate of change with the right graph, where it shows how much change we see at a respective input point, where we see the super transistor utilizing the operational transconductance amplifier current mirror network has the most performance out of all of them. As for the current mirror version of the super transistors, we see that the current mirror super transistors have a wider operating range compared to the single transistor variant in green. We also notice that on top of the wider operating range, they all converge to a sweet spot. This means that on the right graph, this is the rate of change with respect to the input current. So they all have a sweet spot where this point is where they provide the most accurate current for your system. Then for our future work, we're planning on creating a printed circuit board such that we're able to test all of our project in a single chip. And this is to reduce cost and prevent complexity in terms of testing different devices. And then we want to implement the low noise amplifier utilizing super transistors and perform the same comparisons we showed previously. And this one's important. We need process development kits. We need process development kits that have better noise models and have the ability to perform temperature sweep to evaluate our circuits at different environments. Then we wish to integrate these devices into a single programmable chip that allows flexibility for the end user depending on their application. And finally, we are wanting to integrate artificial intelligence into the filtering capabilities so that our front-end system performs better based on whatever application it may be, offering another degree of flexibility. So for a quick summary, our system, when implemented, allows us to run it at a lower cost. The proposed devices perform well at room temperature, so if cooled with nitrogen, we can extract better performance out of the system. We see that the spurious noise filtering options that we have, both programmable and not programmable, offer a great way of reducing system saturation. And then finally, we see that super transistors clearly have an improvement on the performances of devices in which they're implemented with. All right, that would be all from us. Are there any questions for us?
Do you have any estimate of how much cooling you're saving in power, the power cooling?
So in terms of estimate, we don't have the exact schematics of the system. We do not have the numbers of how the system runs. So we've just been given an idea of how it's been running and that it's a closed loop system compared to an open loop. So we've been just designing based on some initial requirements that we drafted during evaluating the premise of this project. So currently we don't have the exact numbers unless we start to coordinate with the Arecibo telescope, which I forgot to mention, we were referring to the Arecibo 12-meter radio telescope for this project, but we have not received schematics of the system to then draw those comparisons.
Though we do have an estimation for the
running cost of
yeah.
the system.
Yes, the other thing is that apparently you have more components than traditional methods.
Yes.
Because you are including feedback and so on. And that's a follow-up of the previous question. Because you have more components, you are generating more heat.
Yes.
So even though you are saving power in terms of the type of transistor you are using, you might have heat from the excess of the components. So that's why
it's a trade-off between performance and air.
It's a trade-off. So do you have any projection of how well are you gonna achieve your objectives, which is
Your question is a good question, and it proves as to why we need to have process development kits that give us the ability to perform temperature sweeps so that we can evaluate that exact problem. Since, as I mentioned, our limitation is that we could not perform temperature sweeps, and we don't have the schematics for the telescope, thus we can't draw a more reasonable comparison to see, okay, what are we saving, or where are we not saving, and where can we adjust? So we need a little more cooperation, not just the process development kits, but we also need from the Arecibo radio telescopes part as well. We need to have their cooperation as well.
Have you identified the development kit that you need, or is this available?
Yes, gallium arsenide is what we're trying to focus on. We don't have any manufacturer in particular. We were trying to get, what was it called? TSMC, was it? TSMC for 16 nanometer using FinFET technology, but we did not get any answer back despite multiple emails. We also tried contacting, let's see, what was the other one? L3 Harris, yeah, L3 Harris we tried contacting, and there's no information on their part either, so we're kind of on a standstill here with silicon and gallium arsenide with ADS.
Yeah, and we have to include that our gallium arsenide PDK does not include PMOS, so CMOS technology is already out of the window.
Yeah, which then limits our integration capabilities, so it's important to have the PDK that's capable of supporting CMOS.
Though we would also accept indium phosphide PDKs. So.
Yeah.
Any other question? Very good, thank you very much.
Very cool.
Where is the mouse? There it is. Yeah, do I have to eject? That's something to be fixed.
You can just pull it out.
Yeah, that's what I thought. But see ya. Oh, no te lo apague. Okay, está bien.
Okay, so now is the turn for the autonomous underwater vehicle for RoboSoft competition for summer 2025.
Huh? Sure. Okay. What did you bring? I don't know, the pen drive they gave me.
Hi everyone, my name is Cesar Cruz, drawing captain of the team Rumarino. Today I've been accompanied by some of my fellow leaders, Angel Cintron, leader of the electrical systems, And Aníbal Rosado, leader of the mechanical systems and also a captain of the team. And obviously, Orde Agustin, ex-captain of the team. So today we're going to discuss Rumarino, who we are, the things that we have been working on this semester, and that's it. This is a little bit of our agenda. We compete in the Robo Sub competition. We're going to talk about the general updates for this semester, the things that each division has been working on, and also the implementation details, and also a little bit of time for questions. So let's start by talking about the Robo Sub competition for last year.
All right. In 2024, we made our return to RoboSub in the competition of RoboSub 2024. First time our model Hydrus has been competing. The competition was divided into two main sections, the design documentation and autonomy. In design documentation, we were scored based off of our video, our technical design report, our presentation in front of a panel of judges, and our website. Thanks to our scoring, we were able to place 24th out of the 41 teams which participated. In the autonomy side, our submarine competed in an obstacle course and was tested on its ability to identify and modify aspects of the field. Here we were able to place 26 out of the 41 teams participating, with our overall scoring leading to being 24th out of the 41 teams which competed in this competition. For general updates on what we have been working on, the team is currently focused on working as quickly and efficiently as possible, leading up to our participation in RoboSub 2025. We continue to learn and create connections thanks to our partnership with IEEE RAS, and make improvements to the submarine at an overall level. To begin with the improvements that have been made during the year in the mechanical structures section, we are currently researching for brand new submarine designs. Currently we have three different designs that are being submitted for professional insight. We have replaced the electronics base of the submarine with a steel base in order to prevent heat deformation, which is a problem that we previously had with our previous base. We have increased the size of the camera connector to connecting the cabin directly to the camera cabin, which has allowed us to get the camera functioning once again. And we have recreated multiple competition objects, with more being created in order to account for competition information ongoing. We are also currently redesigning the thruster mounts in order to create a stronger design. In our next slide, we will show the current draft of the design, and have cleaned up the epoxy on the sides of the cabin hull in accordance to judge recommendations. Here you can see some of the changes that have been made. In the first slide to your top left, you can see the new cabin hull, which has been, a lot of the epoxy has been removed, and the new cable that is currently connecting the camera. On the slide next to it, you can see our current redesign for the thruster mounts and how it looks like on the submarine currently. Below it, you can see our finite element analysis of this piece with a minimum safety factor of 3.78. This is an over 10 times improvement on the previous design. Here you can also see our new base, which has been coated in a material that is non-conductive in order to prevent electrical failures, and two of the objects we have recreated for the course. I will now take you with Ángel Cintron for the electrical systems.
Good afternoon. For the electrical system general updates, this semester we have been working with the power system of Hydrus with the cable management and with an update for our PCB design. Also, we have been doing some research on the signal input-output. Right now, our submarine is working on a two-phase voltage. Basically, we are working on a 15 volts for the jets and a 24 volt for the ESC thrusters for the submarine. Yeah. On our new design for the PCB, basically we implemented a new connection for the DBL to 24 volts As you can see, also by judge recommendation, we added a battery monitor so we can keep track of the battery state through the use of the submarine. Also, in the middle picture, you can see how the cables were before we put these sleeves. So now we have a more cleaner state inside the submarine with the new cable management. It looks a little bit weird, but there basically is the technical testing that we were doing for the servo. Basically, we were testing the parameters for the range, so we have the correct pulse width to adjust the angle of the servo for the camera. Also, thanks to mechanical division, the new addition to the camera tube, now we can pass through a complete USB cable without cutting off, because that causes a lot of unstable connection before. And a new Ethernet cable that we have to make for this competition.
Perfect. Now, talking as a software leader division, in here we can see some of the stats that our team has been working on. We constantly updating the public repository, and we have the issues and the different data that we are currently working on the project. The first thing that we can talk about in software is the architecture. We use something called Docker. So basically, we have different type of computers in our team, and in order to develop a faster way with computer vision and the embedded systems that we're currently working on, we need some type of model that manage the development in a more automatic way. So overall, one of the main things that we have been working on this semester is enabling the Docker wrappers for different type of devices and GPUs. For the computer vision, in here we can see some of the videos and detections that we have been working on. The first thing is algorithm visualizations. For us, it's very important to visualize how the algorithms are working on real time. And if we have the other video in here, we use point cloud estimations. In here, this is like from the back of our lab that we're having some detections. Overall, if we see on the next slide, this is some of the dataset examples that we have been working on. The model is pretty simple, I guess. It's using YOLO models. It's pretty standard on RoboSub competition. We use manual labeling for most of the data, and the thing is that it must work on real time. Some of the machine learning experiments that the computer vision division has been working on has been enabling a new type of model that now is being very popular, called video segmentations models. In here, that was supposed to be a video, but some of the main features that machine learning has been working on is generalization. So now we can be able to select different objects in the competition, and it will detect it in real time through the video. In terms of the embedded systems, we have three main devices. Those are the camera. It's a stereo camera. Again, some of the main things about autonomy is being able to work on real time. So maybe overloading with other type of models for a computer is not the best idea. That's why we use on-device solutions like stereo cameras. We also have an IMU for tracking position on the competition, and a custom AVR megaboard that is just a simple connection through serial communication for two main devices, the thrusters and the servos. And finally, talking about the control system of the submarine, we use a tree-based mission planning algorithm that it's basically a nice way to say that we take into considerations a lot of things during the missions, and if something failed, we can track it and have another solution for it. We have an ASCII, then we have a real-time server listener for thrusters. So basically the controller is a proportional type of controller feedback solution. So it takes the IMU data and it will track with the correspondence of the detected objects, and it will try to approximate to the correct position. Then we have the real-time servers listeners that are just taking from the controllers the data. And now we're going to talk about how we managed to get into the competitions, right?
Yeah. So first of all, apparently you can corrupt the file, so pardon those little errors on the text. I'm going to be talking a little bit about the business operations side of things. As a previous captain, I've been helping the team just keep their flow with everything administratively. In part of the business operation type of things, we had a panel with different RoboSub teams from 2024. We communicated with teams from Alberta, Canada, Arizona, Florida, and we had like a nice little chat like, hey, what are the type of challenges you guys have faced? These are challenges we faced, and we just helped each other learn from that experience. We've also done like some pickleball tournaments. Pickleball is very popular, and we don't want the guys to stay in the lab 24/7, so we're forcing them to go outside, get some sun. We had a tournament in December 7th, April 4th, and 5th, and you're still in time to register for our pickleball tournament in May 10th. So if you're interested, there you go. We've also been doing various pizza sales to get funds for the team in case if we need to make any emergency purchases, and that money will help us during the competition if we have any other emergency purchases as well. We've been doing some outreach events, get the high school students motivated in engineering, not just robotics, but engineering and what we do here in the UPRM. We've gone to Colegio Sagrado Corazón and the Specialized School of Science and Technology and Math. And one of our members actually participated in Lily Day as they were a previous intern. And some preparations we've been having for RoboSub 2025, like Aníbal mentioned before, we're judged based on technical design reports, our website, or video. So we're working on creating the video and getting everyone star ready for their debuts. As new fresh faces are going to be in the team, we want to get them prepared for all this type of glam light, I guess, if you want to call it. We also want to make sure that their technical design report is done on time and they're not rushing it like I did, and make sure they have everything that they need, diagrams, any explanations, appendix, everything that the judges are looking for, make sure it's accounted for. We're also going to edit our website so it doesn't look like the bottom text, and make sure that doesn't happen. Make sure our domain is also up and ready with our updated website. And we're going to be doing an Owning the Depths workshop. This is basically just a pun on our We Own the Depths catchphrase. Students that are going to stay here in Puerto Rico because they're working nearby, they don't have any internships or anything, they're going to be here working, giving those last touches on the submarine, getting it ready for the competition, while also working on the pre-qualifications. The requirements are basically doing the first half of the competition, which is basically detecting a gate, going through it, identifying a buoy, going around the buoy, and coming back to the start gate. And we submit that video at the end of the summer to the panels, and we get the pre-qualification. Then we're all good. If not, we can qualify during the competition as well. Lastly, we're also working on the logistics for the plan to get to California. It's a very expensive trip. Puerto Rico to California, it's approximately 12-hour flights if you don't count the scales. And we're planning to send 9 to 10 members like last time. So we're getting all the housings, the diets, the plane tickets, the transportation, everything they might need. We got to send the sub over as well. And a main issue from that is like, how do we transport a 23-volt battery through an airship? You can't. You got to either find one over there or just fray it 2 months in advance. So those are the challenges that we're doing while we prepare for RoboSub 2025, and our team is working on that logistics. With that, I want to thank you guys for listening, and thank you everyone here for the sponsors, not only for our team, but for the IAP program. Without your help, this wouldn't be possible. Thank you. Any questions? All right. I'm 2 for 2. Let's go. Se me fue el mouse. No, like. Yeah. Bruh. You know what?
I think it's just kind of, oh, that's a,
Our next talk is power line inspection with infrared equipped drones. Our students are Alexis Morales and Daniel Nieves. No me la cierre, déjala abierta para que los demás puedan. Esta fue la última que tú enviaste.
Okay, so good afternoon. My name is Daniel Nieves, and accompanying me is Alexis Morales. We're going to be showing a presentation on infrared inspection lines with drones. Power companies need to regularly maintain data on how the power lines are working. In order to do that, they need to have sorry. They need to check irregularity in the power lines. Inspecting these power lines that are next to roads in cities and towns is relatively easy, but for more remote areas like on top of mountains, it is more complicated. In order to do that, they have to manually send the team or spend money to fly a helicopter in order to reach those more remote areas. This project aims to reduce the cost of those inspections by sending a drone. The drone will be equipped with an infrared camera that could possibly detect any anomalies that are occurring in those power lines.
Okay, so every device, such as connectors, transformers, and lightning arresters, are connected to this equipment via a connector that is tightened with screws. Over time, due to contamination, a hotspot is created. Not only because of current, but contamination also creates this hotspot. With the expansion of metals due to high temperatures, these connections loosen over time and create a high impedance hotspot which becomes hotter than normal. That's when power companies know that there's an irregularity in the temperature, and that's when they know that there's something wrong with it. That's when they would fly a helicopter or send people out to check it. Since the project was for a class, we decided to use our own drone. This is the Holybro X500 V2, a lightweight, high-performance quadcopter frame built for research and development. It features carbon fiber arms and nylon side plates for durability and low weight, a modular design for quick assembly and maintenance, compatibility with PX4 and ArduPilot flight stacks, and a large mounting area to accommodate custom payloads like thermal cameras and a Pixhawk. Speaking of the Pixhawk, we used the Pixhawk 6C to connect the GPS, the telemetry, and the 4 motors. To power all of these components, we used a Bashing 6800 14.8 volt battery that we connected below the drone. We managed to connect everything without compromising stability of the drone, and we were able to fly it without any issues.
As for the controller, we decided to go with the Radiomaster TX16S Mark II, a radio controller for our drone that has multiple switches and buttons, which enables us to switch between different flight modes for the drone. These include but are not limited to loiter and return to launch. Loiter is for the drone to be stable in order for us to have a better image of what we're capturing.
For the infrared camera, workers normally use an infrared sensor shaped like a gun that uses a laser pointer, which they point at the object they want to check, and by pulling the trigger, then it tells them the temperature of the object that they pointed with that laser. The camera we used is a Vivor thermal imaging camera, which we mounted on the front of the drone looking down. The camera can start recording before flying the drone, and it will keep recording until the user stops it themselves. While this feature is helpful, the biggest advantage of the camera is that we can connect to it via a wireless connection that the camera itself creates, like a Wi-Fi connection that the camera creates, and you can connect to it via your phone. Then you can see a live feed of what the camera is showing, and you can manually take pictures from your phone with the camera itself.
We did tests with the camera by taking pictures from below, and these proved that it was working as expected. It also displays the hottest and coldest zones shown by using the red and green numbers respectively. Finally, it shows the current emissivity with the number next to the battery power, and the central point temperature with the white numbers on the center on the upper left corner. While taking these pictures, we noticed that the heat coming from the concrete and asphalt would overpower the whole image. We theorized that the surface area of the hot object was so big it interfered with the readings. Then, while we didn't encounter the problems ourselves, the power plant emits a electromagnetic field that could possibly be a concern when flying the drone.
When we compared the pictures taken from above with the ones taken from below, we found that the latter displayed the temperature of the objects in focus more accurately, thus confirming our theory of thermal diffusion. We tried to change the angle of the camera to take pictures from straight ahead, but this proved difficult since the only place that we can actually place the camera, it only has a handle on the bottom part of the camera. So we would essentially have it connected to the drone, but it would be just hanging and dangling, which compromises the stability of the drone itself, and it will not let us take more stable pictures.
After reviewing the images, and we discovered that thermal diffusion, final findings, I'm sorry. For the future of this project, improving the resolution and zoom of the camera would help detect the hotspots more accurately. Changing the camera angle to record straight ahead could also give us a better angle when taking images of any irregularities we may find during the power lines inspection. For the, yeah, I did that already.
All right. So for our unfinished improvements, we had started working on some improvements already. We had bought a thermal camera, as you can see here, a FLIR boson camera module, and we had purchased a Raspberry Pi Zero. Our intention was to connect the FLIR boson camera to the drone with a tripod mount that it came with and some screws. However, this semester came with some complications which didn't really permit us finishing these improvements. The Raspberry Pi Zero was also to be able to connect it directly to the camera and have it automate the recording process and save the footage to the micro SD card so we can then review the footage later on our computers. For our project management strategy at the start of the semester, we created a Gantt chart to help us keep track of our progress with the project, As we mentioned before, this semester has come with many complications, which have made it difficult for us to precisely follow the timeline, but we've been able to accomplish 90% of it. If you would like more information on the specifics, we would be happy to send the Excel sheet with the exact dates and explain more of our difficulties with the timeline. Finally, we have a breakdown of the cost of materials. The total cost of everything was $1,124.97. We had some extra expenses with the FLIR boson camera module and the Raspberry Pi Zero, but ultimately decided not to show them here in the presentation since we weren't able to finish those improvements. Even so, we do have the cost of each component right here with us. The FLIR boson camera module package cost roughly $2,500 with the package protection guarantee, and the Raspberry Pi Zero starter kit cost more or less $38, bringing the total cost up to $3,694.99. However, this number includes the VVOR camera, so the cost would be less without it, specifically $3,412. Compared to spending money every time a helicopter needs to be sent, this would be a one-time payment since the maintenance costs are a lot lower than that. Any questions? All right. Thank you so much.
Yes, Alexis, can you explain how you detect using the camera? How can you pinpoint the hot spots?
With the thermal camera?
Yeah.
Yeah. So the hot spots, as you can see, let me put right here. So as you can see from these pictures, the camera has itself a thermal guide on the right side, and then the object on the center, which in the left it says 26.5, on the right says 37.2. That's the exact heat of the object in focus. The hot spots would appear as the red objects on the pictures. Since the heat from the roads was so big, that gave us thermal diffusion, so that's why in the pictures you can only see heat coming off of the roads and the concrete. That's why we wanted to implement a camera facing forward instead of facing downward, so the thermal diffusion wouldn't be as big. So the camera itself only can detect the hot spots with the red objects. Basically, yeah, right there. If you can see, the power line appears red, that's a hot spot.
Right. And the other picture, can you tell, is the station was on or off?
No, the station here was off. We didn't get a picture of the station having turned on because of the difficulties with the semester. We weren't able to actually go over there to the power plant while it was on, but it is our intention to do so for the future references.
Any more questions? Thank you very much.
All right, thank you.
Our next presentation is 3D mapping using unmanned aerial systems, AID. The student is Angel Rivera Rodriguez.
Good afternoon, everyone. I'm going to be presenting my project 3D mapping with UAS AID. This work explores how drones can support terrain modeling and mapping operations with modern tools like photogrammetry and LiDAR data. Mapping large or complicated areas presents serious challenges. Traditional field work is time-consuming and labor-intensive. In rough or hazardous terrains, it can even be dangerous. Often, if something is missed, teams have to revisit the sites, and it can cost more time and money. And in areas that are remote or expensive, the efficiency of manual methods drops significantly. This project investigates how drones can offer a better solution using custom-built drone platforms. I aim to make modular systems that could support both camera and LiDAR sensors. These tools combined with software like OpenDroneMap and Cloud Compare allow for safer, faster, and more accurate data acquisition. This is the drone I assembled. It has a Tarot 680 Pro drone frame. It's a hexacopter. It has two 6S batteries with powering 40 amp ESCs, 6 motors. The flight controller is a Pixoc 6X Pro, which allows full GPS support, autonomous mission programming, and telemetry monitoring. The system is designed to support swappable sensor payloads and it's flight ready. In this project, software is the most important thing to have. I use OpenDroneMap for photogrammetry-based 3D model generation and Cloud Compare to analyze all the data from the LiDAR, which is a Unitree L1 LiDAR sensor. I also configured Mission Planner for autonomous missions and Lich for DJI-based image collection while the custom drone was being finalized. These tools allow processing, mission control, and data visualization in streamlined way. The system includes an A6000 Sony camera, which provides us with high-res compare to analyze LiDAR data. I also configured the Mission Planner for autonomous missions and Lich for DJI-based image collection while the custom drone was being finalized. Okay. This is basically, since I couldn't integrate it fully in the drone, basically I used the DJI Air 2S drone to capture images while it was being built to test whether OpenDroneMap or WebODM can process all the pictures. This is in an area behind the university. Basically, it's very high quality, but with the integration of the LiDAR and bigger sensors, we can have more high quality pictures to stitch them together and make a 3D model. As for the LiDAR, I also validated the LiDAR independently. As you can see, it produced a high-density 3D point cloud. Once mounted, the data can be merged with photogrammetry outputs in Cloud Compare. So what's next? We have to integrate this into the drone frame, the LiDAR sensor, and synchronize it with the cameras. With that in place, the platform will be ready for full deployment for dual sensing mapping missions. As for applications, this system can be used across many industries like civil engineering, for land development and planning, for land surveying, for field assessment, utility companies for infrastructure inspection, and emergency response teams for documenting disaster zones. The drone platform provides flexible, efficient, and cost-efficient mapping support in all these areas. My biggest challenge was time. Time was the biggest constraint. I wasn't able to fully integrate the payload before the deadline. I also had to solve issues with power delivery and communication between the components. But along the way, I gained valuable experience in drone assembly, safety configuration, mission software setup, including Mission Planner, Open Drone Map, and Cloud Compare. In summary, a prototype was built, a very good foundation. Although the full sensor integration is the next milestone, the result from separate tests show a strong 3D mapping potential. I now have a working platform and all the tools needed to be ready to fully deploy the unmanned aerial system. I'm happy to answer any questions. Thank you.
Can you give us an estimate of, once you acquire the images, how much time the software needs to create the 3D model?
It mostly depends on the RAM. If it's 8 gigs of RAM, it took an hour. If it's 16 gigs, probably 36 minutes.
So do you integrate both sensors? Do you integrate the LiDAR and the images, or are they separate sensors?
For now, they are separate. I had a lot of complications in the integration because most of them is open source.
Okay.
So we have to like build the software from the ground up.
Okay, so from the LiDAR you get the point cloud, and from the other one you get the image. Okay,
yeah.
okay, thank you.
Any more questions? Thank you very much.
Thank you.
Our next presentation is Hybrid Architectures, Symbolic Parser, and Neural Lexicon. The students are Jimmy Carrero, Carlos Leiva, Kevin Bonet, and Surisadai Esteves.
Well, greetings everyone. My name is Surizada Esteves Cruz. Here to my left we have my team member Jimmy Carrero and also Carlos Leiva. And today we will be presenting to you our research project HAPSNO, which stands for Hybrid Architecture, Symbolic Parser, and Neurolexicon. Our advisors are Dr. Hilton Allers, Dr. Naida Santiago, Dr. Christopher Font, and Dr. Fernando Vega. To share a little bit of background, modern computational systems lack three things. They do not possess syntax rules, in this case syntax with capital S, referring to syntax in linguistics. They do not consider grammaticality nor ambiguity. And just to make the side note, grammaticality does not only mean sentences that are grammatically correct, it means anything that humans can naturally produce. And lastly, they do not model language as a cognitive system. Throughout history, computational systems have been unable to process natural languages like we humans do. We tend to do that process subconsciously. We believe that the implementation of natural language theory within a computational model will help us and give us insight on how to solve this problem.
Particularly regarding our problem, if we want to define it better, it would be that computational systems are inadequate when processing the ambiguities present in natural languages, natural language being at the core of what we're trying to research. Furthermore, there exists no integrated biologically possible computational model of human language that allows for testing of our current linguistic theories. We have a lot of pretty good theories on how language works in the human mind, but no feasible way of testing them that doesn't require a lot of probabilistic methods that aren't really how the human mind works. So building on top of this and on previous research, we hypothesized that building and integrating the components of human language cognition in a computational system should provide a better way for computers to process natural languages and should also allow us to test current syntactic theories. Now, as for more precise objectives, it would be the main one to model human language cognition by developing a biologically plausible model. Now, what would this allow us? Primarily, it should allow us to execute grammaticality judgments. This would allow for a more certain approach towards correcting grammaticality, and as my partner mentioned earlier, not grammaticality as in style, but as in is it feasible to produce by a human being in a natural way. And it should also allow us to test the syntactic theory, particularly by implementing the strong minimalist thesis. The strong minimalist thesis is, so in a matter of way, we imagine the ideal scenario. What does this system look like in its best scenario with the least amount of dependencies in its most isolated conditions? What is in its purest state and its purest and simplest state? And we work making the assumption that that is what we are going to work towards. And while we are building towards that, if we find there are any components that we need because of certain limitations, we add them. But in principle, we are trying to only use those components and pieces that are strictly necessary. That's why it's strong and minimalist. Minimalist because we're only using what we need, and strong because we start off only using what we need and nothing more. Furthermore, we want to develop a system. This system should also be capable of dealing with ambiguity in natural language. It's more of a side effect of being able to produce grammaticality judgments, but it should detect lexical and structural ambiguity through possible syntactic representations and utterances. When given an utterance, the system should be able to return all possible syntactic parsers, and through those be able to identify ambiguities in the utterance. Now, how we're doing this is language consists academically of a lexicon and a grammar. Lexicon being the units or the words, if you want to call them that a language has, and their syntactic features, while the grammar is the set of combinatory rules that allow us to merge those units into larger structures. This is modeled into our project HASNO through the following components. We have the lexicon, which is in the part that said the lexicon. So it serves as a knowledge base of linguistic features for all lexical items in an utterance. You can think of it like a dictionary. It has a word, in which it might be bigger than a word, the unit we're talking about, or it might be smaller than a word, and its corresponding syntactic features. And it has the symbolic parser, which we're basing our project under the assumption of UG, universal grammar, that all languages share a common grammar, a common set of combinatorial rules, and that difference between languages stems only from differences in the lexicon. So all languages ranging from English, Spanish, Japanese to the most ancient or future languages should share the same grammar. The only differences should be in the lexicon. And this lexicon contains the grammatical rules to unify the features contained in the lexicon and produce all valid parses when you are given an utterance. These two components are aided by a corpus, which contain the tagged examples of ambiguous and unambiguous utterances, so the system can know how to identify each one, and a base for the lexical items in the lexicon, and for training the probabilistic encoder. There is a probabilistic component to this project so as to determine which parse is more likely to be the one that is being referred. And going to the probabilistic encoder, it consists of a pre-processing pipeline for adequate processing by the symbolic parse. Even though we humans can process words naturally, computers can't, so we need a pre-processing segment that can translate those linguistic units to computationally viable units. Finally, we have the likelihood estimator, which determines the likelihood of each parse produced by the symbolic parser. And by likelihood, we mean how likely is it that that is the one that was meant to be used in a certain scenario.
Hello. So here we have a visual representation of the pipeline. It's a bit complex, but breaking it down, we have as an input the utterances, which are essentially the string of, you could call them sentences, but if they're not grammatical, then they're not sentences. So anything that it can be said. And then the next box we have the data processing, pre-processing, which is essentially we're taking this string, this input string, and trying to convert it into a structured representation that the parser can then use to combine and generate the structure of a sentence if it's grammatical or not. So yeah, in this pre-processing, right, there's several steps, right, that help us in lexicalizing that input, like name entity recognition. This helps us in identifying names, so people or nouns. And we also do tokenization, so how do we separate from this string the words, separate between words, and this helps us discretize to separate these into lexical items, and then fill in all these features that are needed for the parser to use to combine and generate the structured representation. So these features all come from the strong minimalist thesis in linguistics, and yeah, so we have to do some morphological analysis and use a lemmatizer as well to get all these features. And once we have the necessary features and we can also check if these lexical items have already exist in the lexicon, so we can reuse them. Or we might also have to predict features that we haven't seen before that don't exist in the lexicon. So there's lexical items that can have, so there's words that can have multiple lexical entries. And this is where ambiguity comes in. So we can have the word saw, it's a verb. You can see, or you can do, like saw something, right? Cut something in half. So that's an example of some lexical ambiguity of the same type, so they're both verbs. But you can also have ones with different types, like the word can, which can be a modal or a verb. To can, to put something in a can, or I can't do something. So there's different types of ambiguities that this system inherently solves. And yeah, we then pass this structured input into the parser. And the parser uses this input, combines them, and generates all of the possible interpretations in the form of a structured tree. And once we have all the possible interpretations, if there are any, if there aren't any, then the sentence is not grammatical. If there's one, then there's only one interpretation. If there's more than one, then the sentence is ambiguous, and we have one tree structure per each interpretation. And then we can pass this through the likelihood estimator and generate a probability estimation or likelihood estimation of the correct interpretation given the context. So yeah, untagged input, lexicalizing, passing to the parser to generate the tree, and then estimating the likelihood of each interpretation. So in the lexicalizing process, if we haven't seen the lexical item in the lexicon before, then we're going to have to make use of a probabilistic encoder. The probabilistic encoder essentially takes what we've seen before from our corpus, which is like our data set of sentences that represent different from ambiguous sentences to non-ambiguous sentences, and all of their features and lexical items in the lexicon. And we use this to train an encoder which predicts all of the features of the lexical items from the part of speech to the, let's say, if it's plural or singular, and different features that are necessary for the parser. And then we have the symbolic parser, which takes all of these lexical items, combines them using the strong minimalist thesis, and then the likelihood estimator, which takes these tree interpretations, and based on Bayes' rule, we can generate a probability that of the likelihood of each tree, based off of rules to regenerate the tree. So if we have a noun phrase and the rules that usually make up a noun phrase is a determiner and another noun, and then we might have a smaller amount of rules that have also an adjective there, then the one with a more common structure would have a higher likelihood of interpretation. Oh. And the expected results are this.
Yeah. For the expected results, so we expect our model to do the following. It should be capable of executing categorical grammaticality judgments. It should produce all possible syntactic representations, or in other words, syntax trees, that for any utterance that is given, such as Sherlock saw a man with binoculars. It should estimate the likelihood of each interpretation, like my partner Leva was sharing, and it should also disambiguate structural and lexical ambiguities in utterances. As we can see from the example here, we have the utterance, Sherlock saw a man with binoculars. Just to make a note, an utterance is more than a sentence. It's something that you say verbally. So you can say dog, and that's an utterance. So in this case, for Sherlock saw a man with binoculars, we have two possible trees. That's why it's ambiguous. In this case, it's a structural ambiguity example, because we can have, for example, the tree on the left, which represents Sherlock saw a man with binoculars, which would be the agent Sherlock seeing the man with binoculars, and the one to the right indicating that the man is the one with possessing or holding the binoculars and seeing Sherlock with the binoculars. Just to share the timeline for our project, we divided it into the following dates. From September to October 2024 is the literary review. From October to December 2024 was the system design. From January to April 2025 was implementation and testing. And lastly, from April to May 2025 was the documentation phase. Now, to share the current status of our project, just to highlight, our project is divided into 3 teams, which is the encoder, the corpus, and the lexicon. As previously mentioned, the encoder, which is the one in charge of the model's code, implemented the pre-processing pipeline with the following components: name entity recognition, standardization, tokenization, parts of speech tagger, morphological analyzer, lemmatizer, and the lexicon feature lookup. Right now, since they finished all these steps, they can now begin commence the integration of the symbolic parser in their development. The corpus team, which is in charge of making the sentences to train the model, they have finalized the tagging system for the HAPSNO project, which now includes the necessary categories for the Spanish version of the adversarial testing corpus. They elaborated, completed, and verified 2,020 entries for the English adversarial testing corpus. Additionally, they expanded the English corpus to include additional test cases. And lastly, they elaborated and verified 2,020 entries for the Spanish adversarial testing corpus. The lexicon, or like my partner Jamie shared, which is the base knowledge, or let's say the dictionary of the model, has identified 332 verbs that are present in the corpus, and with their respective subcategories, transitive, intransitive, unergatives, and unaccusative verbs, C selection, and their theta roles. They also identified 429 nouns with their respective class, such as common and proper nouns, subclass, human, animate, inanimate, time, location, emotion, and personifiable, count mass nouns, arguments, and including their 5 features, if it's third person, singular, plural, or all those features, right? And they have lastly identified 46 prepositions present in the corpus with their respective theta roles.
Although at the moment most of the components within the system have been mostly finalized, the entire pipeline right now hinges on the parser and the lexicon being completed. As of the moment, what you see here is pretty much the final state of our project as of right now, where we're predicting those entries that are not present in the lexicon. So you can understand what we're seeing. The system was given an utterance. In this case, the utterance is what solution did he bear, where that utterance contains ambiguity. Now the system, it's trying to identify the probability, it's trying to assign a probability and a tag to each one of those lexical units. So for example, the first one, which is what, it's saying that the most likely tag or part of speech tag associated with that item is a WH pronoun with a 99.83% probability assigned to it. Solution is also a noun, is most likely to be a noun. Did is tense. And he is a pronoun, and so on and so forth. All of these are assigned a tag. The next step after the system generates these tags would be to use the parser to identify which combination, because it doesn't just give us the main tag. The system generates multiple tags, all possible tags, and we would then pass all those possible tags to the parser so that it can rule out those tags that cannot be combined and thus are ungrammatical. So there is no possible way to make that the utterance could have been built using that structure. As of right now, we're in this stage where we have those unknown words and known words being assigned a tag, and next up will be joining this step with the parser, which is currently being worked on in the University of Arizona by Dr. Sandy Wei Fong. Yeah, that's pretty much where we're at right now. So for future work,
for the lexicon, we should assign the theta roles from deverbal, deadjectival, and picture nouns. We also do recommend to also previously revise previous work from our earlier team members, such as adjectives, adverbs, determiners, complementizers, tense, pronouns, coordinators, and degree. And lastly, we should start working also with the Spanish lexicon. For the encoder, as mentioned previously, they should also commence the integration of the symbolic parser. And lastly, the corpus should continue the development of the Spanish corpus. Any questions?
Yeah, thank you very much for the presentation. It was great. I have a question about the example just that you mentioned. Yeah, that's that. You said that it's a question. You said that it's ambiguous. Could you explain why is that question ambiguous?
The ambiguity within this one is more of a lexical ambiguity more than a lexical one, than a structural one, because we have the word bear. In this case, bear is what we call a heterocategorical ambiguity, because it's a single unit that can have multiple tags. It can be bear as in to bear, the verb, or it can be bear as in a verb, bear the noun. So if we take it that we mean bear the noun, this would not really make sense, because we will be asking what solution did he, and then just put a bear. I mean, it's like naturally, a speaker would not think to ask that question, so it's less likely. Not saying it's not possible, but wouldn't feel very natural, as opposed to treating it as a verb in which you're actually requesting information regarding an action that was made, with the verb being a verb. Any other questions?
Just thinking about applications to it, can you explain some applications?
Yes. While the focus of this project is mostly the advancement of science and academic knowledge, because the foundation of this is trying to test our current syntactic knowledge. However, some practical applications do include advancements in computational linguistics, particularly when it comes to natural language processing, because instead of having to use probabilistic approach to generate or recognize grammatical language, right now pretty much all of us are familiar with large language models, and that they're very good at parsing and generating what we call natural content. To get to this point, we have had to spend and utilize a ridiculous astronomical amount of data and energy to train these models to be as accurate as they are. However, since our approach is not a probabilistic approach but a rule-based approach, well, yes, we do use probabilities and different estimations, but those are more for the final step, which we're trying to interpret which is the quote-unquote correct utterance. But the entire process is rule-based, so that would eliminate the need for most of the computations, and furthermore, the need for the astronomical amount of data, because while current models base their estimations on the relationship between words, they need a lot of relationships to analyze. This one, it's rule-based, so it will know, regardless of if it has or has not seen the lexical unit, whether it can be mixed with any other unit beforehand. That is what we consider to be the main use. However, it could also be used in, for example, legal cases where you're reading a document and it's like, hey, this is an ambiguous document. And you're trying to do a legal defense, like, hey, what could this mean? Did you mean this or did you mean that? And based on the document, it should be able to say, hey, these are the two possible interpretations or the two possible parses. And context-wise, using a little bit of math, this is most likely the one they meant. But as of right now, the main use of this in its current state, I'm not saying it cannot be used for anything else, but in its current state, its application would be furthering the advancement of science and cognitive science, and we know it particularly pertaining to human language and natural language processing for computing.
I want to add something to that. So yeah, a huge point in an advantage of a system like this is in reducing data requirements. So if you ask ChatGPT, and we've done this a lot at the lab, ask ChatGPT to explain all different interpretations of a sentence. In a bunch of the cases, it fails to do so. And in cases where, like in legal cases or medical cases where you want to understand what the model is interpreting, right? So this is the advantage of explainability as well as reducing data requirements. You want to know what the model is interpreting and be able to evaluate the results, which is a lot easier to do so. Then you're going to need a system that produces language in the same way humans do. You can't use a transformer-based model to. You could use a transformer-based model to generate all possible interpretations of a sentence, but you're not, since it doesn't include all of the rule-based knowledge that we have of language, there's no guarantee that it will actually produce the correct interpretations. And if there are no correct interpretation, then it'll most likely just generate, hallucinate and give you some incorrect one. So in situations where you have less data, less compute, and being able to understand what the model is interpreting, this system is needed for that. Yeah, we can't rely on current tech, which is based off of just pushing a lot more data and compute and money to the problem. This is a much more theoretical problem.
Thanks.
I also would like to add now a little bit more to the linguistics side. We're not working with a field, as we call in linguistics, called pragmatics, which is the knowledge of the world. Right now, the way that we detect ambiguity is through syntax, which, as I mentioned, in other words, would be how we organize words and phrases to make sentences. So our program doesn't really generate sentences. It's more an analyzer. We're not making a synthesizer. So in other words, we give them the program a prompt, it analyzes it, and it detects which ambiguities it may possess and makes syntax trees out of them. So again, it's not like common AI where you give it a prompt and it answers you a question. No, we are giving the AI the sentences so it could analyze it and tell us, are there any ambiguities within this utterance or this prompt?
And another point that I completely forgot, thank you, Leva, for mentioning it. Thanks to the minimal amount of data necessary, quoting Dr. Allers, he said that the strength of large language models is also its weakness. It needs astronomical amounts of data to rely on, but what happens when the data doesn't exist? When we're talking in the field of linguistics, sure, Spanish, English, and Chinese all have a lot of representation in the virtual world of data. However, languages like Navajo and Nahuatl don't really have any representation. So how are you going to make a large language model out of a language that is not large? Our model, since it's based on the grammatical rules, should be able to, hey, as long as you give us some lexical units, it should be able to work at the same level as a language with more data available.
And I'll keep this short. But also the fact that the reason why it uses a lot less data than typical transformer-based model or probabilistic models or other method that exists nowadays is because in the theory of linguistics that we have, modern theories, SMT, it reduces the learning aspect only to the lexicon, whereas transformer-based models don't do that. And the reason why you need astronomical amounts of data is because it's also learning the syntax through these data inputs. And in our model, the only learning that is being done is in the lexical items. Yeah.
Thank you very much. Our next presentation is a smart carpooling system for UPRM ROCS. Jose Rivera, Lorenzo Castellini, Carlos Pepín Delgado, and Christian Rivera. Okay, no lo vas a ver aquí. La vas a ver en la espalda. Ah, no te voy en el PowerPoint. No, no te problema. Lo que pasa es que van a estar hablando. ¿Dónde está? Sí, pero no me lo... Ves que no está proyectando. Entonces tienes que pasar esta ventana allá. No, porque entonces me daña la presentación de PowerPoint. Sorry, me acabo de decir. ¿Cómo lo hacemos? ¿Qué? Al otro.
Good afternoon, everyone. I'm Carlos Pepin Delgado. I have the honor of kick off this presentation on behalf of the ROCKS Smart Carpool team. With me, Jose Rivera, Lorenzo Castellini, and Cristian Rivera. Each of us are bringing our expertise in back-end, front-end, full stack, and hardware integration. We'd like to also briefly thank our faculty advisors, Dr. Anaida Santiago from Computer Engineering, Dr. Daniel Rodriguez from Civil Engineering for their guidance and support throughout the project. With that, let's talk about the project. Our campus, like many others, faces some serious challenges. In instance, limited parking availability, frequent traffic congestion, and unequal access to transportation for many students. On top of that, single occupancy vehicles are a major source of pollution and inefficient space use. So with that, we ask ourselves, how can we create a sustainable, inclusive mobility system that addresses these issues and without relying on costly solutions? So we created ROCKS.
So like Carlos mentioned, to solve these problems, we decided to develop an application, a mobile application to be exact, that is both available in iOS and Android. It is free to use to all UPRM students, and its main task is to give rides to students that may have problems with their car, may not have transportation, they might be freshmen, they don't have the parking permit, and they can go from campus to campus, and this opens a whole world of possibilities because it can help many people and it can also be integrated to existing transportation, so it really helps people to get around, Mayagüez, which is known as a university town, and this also we have also been thinking about the project, and this also opens a whole world of possibilities with other projects. And so this project is, very wide, and it touches upon a lot of topics and a lot of aspects. So, really the world is the limit with this project, and it also solves many of the problems Carlos mentioned. Apart from the main task, we're also tasking, reduced congestion, which also helps all of the citizens in Mayagüez. We're also, targeting sustainability, which is very, it's a topic that is now talked about a lot in engineering. So, this project is very well-rounded.
Okay, so now let's talk a little bit about the system architecture and how we actually implemented this design. So starting off, we have the hardware. On the top part, we have the mechanical arm, which is what sort of locks people out of the parking. So the main incentive to give a ride in this system is that you get a parking spot when you get to campus. Now, the mechanical arm, the function is to lock people out of the parking so that we can have control over that. It's controlled by a Raspberry Pi, which communicates with our application API backend, which is hosted in Microsoft Azure. Additionally, we have a solar panel, which the main purpose is, first of all, it's sustainable, so we don't actually have to use much electricity, as well as, with constant power outages, the Raspberry Pi actually has constant access to electricity. Additionally, we have the application, the actual app that the user downloads, which is written in React Native and is available, again, on both iOS and Android. Additionally, we have our services. So we have the IoT Hub, which is what we use to communicate with the Raspberry Pi. The main application is the API, the backend, which is what communicates the front end to our databases and allows users to actually use our application. This is written in Python and Flask. We also have the optimization algorithm. The optimization algorithm is an algorithm that was designed by students and a professor in the industrial engineering department. What this does is it takes information in matrices of users. It takes in their distance from the university, it takes in their location, and also takes in the time intervals that are used. We can't sort of map everyone down to the minute that they want to get here. So what we do is that we round it down to the nearest quarter of an hour. So let's say that you want to get a ride at 7:07, then you might actually get a ride at 7 o'clock, and it makes the computation more efficient. Additionally, we have the cost calculator, which uses the Open Route Service API. This just gives us information on distances and is what we use to create the matrices that we feed into the optimization algorithm. And lastly, we have the communication services, which is what we use to communicate with our users. Mostly this is just used for account verification. And lastly, the MySQL database, which is just where we store all of our data. Following that, we have...
Okay, so for this semester and this year, basically our main goal was to get the whole team in the same picture. So we decided to, restructure, to start from a clean sheet, and we decided to start with documentation because that's something that we will talk upon later, that documentation is super important, and we learned that kind of the hard way. And so we documented the code, we documented, all of the bits and details that everyone needs to know so that when we onboard someone else, it's much easier because, if not, it can be a pain and it can take time and it can really slow down the project. So apart from that, we also refactored some key front-end components, which is something that we also learned because we had the problem that many of the dependencies that we were using with React Native, they actually were deprecated, and so we had to restructure, we had to basically manually adjust the environments, the dependencies, and all of that. And below, you can see that we attached the images that we were able to recover from the app. So that's basically the app after the refactor. So now it will be much easier to incorporate many other front-end and also back-end. And we also refactored the back-end code, so it's easier to read and it's easier to maintain, and it's way easier, and we can also modularize it, and that's something we also did. We also containerized local databases, which makes it easier for us to develop and test new features. And we also implemented some quality of life features, so we implemented stuff like friends, blocks, and all that stuff. And yeah, that's basically it. Basically, this semester we wanted to set the goal, and now we can carry that momentum into the next semester and future semesters.
For plan modifications, right now we're currently in the brainstorming / feasibility phase on how to implement an individual parking barrier system. Right now, what we have is a single barrier / gate which controls access to all of our reserved parking spaces. Our goal and what we're looking to achieve is to have individual control over a parking space in order for the user to have a designated spot when they arrive. How are we going to achieve this? Well, as you can see in this diagram, the barrier arm mechanism will be connected to a motor, which is controlled by the control unit, which could be a Raspberry Pi, which receives a signal from the app and determines whether to hold position or to give access to the car. In addition, a sensor could be implemented so that we can easily implement safety measures, so when it can detect whether an object is on top, where a car is parked, and make a fail-safe so to make sure the barrier doesn't go up when the car is parked. Other key design considerations are for it to have an easy, non-invasive installation. A surface-mounted design would be ideal since it would reduce costs and will be easy to implement. Additionally, we're looking for each individual unit to have its own weatherproof component box, which would contain the set of the components mentioned here. And finally, for it to be sustainable, each unit will have its own battery paired with a solar panel so that can be charged.
Some additional modifications that we are thinking about implementing are changes to the algorithm that we use to match people together. Right now, the only information that it takes into the algorithm is only distance and the time in which someone wants to arrive or leave. We have also thought about implementing changes such as preference informed matching, which takes into account not only your actual factual distance and time, but also who you are as a person and if you would enjoy rides with certain people or not. Additionally, we also have another feature such as ride splitting. So right now you can only take both rides, right? You take in an arrival ride and a departure ride. Implementing a one-way ride would make it more available for everyone that wants to use it. And also we want to do some changes to the cloud infrastructure. We use a lot of services that are sort of third-party, such as our messaging services, which we use Vonage API. But also Azure provides us with these services, which is where we mostly host most of our services. So something like using the actual Azure messaging services, which is made to be compatible with the other services that we use, would make it much more easy and feasible to create more features.
While working on rocks, these are some of the lessons we learned along the way. First, document knowledge transfer is essential. Without proper documentation, progress slows down as new members try to catch up on early material. So that's something we'll prioritize going forward. Also, taking the time to understand the full picture, the full system architecture without prior getting into the task. Because if you made a change in a component and you don't know how this will change all the system, hypothetically it could damage the project. Also, test early and test often. Every single component, you gotta make sure it works to detect early some issues that can harm. So if you make sure that works before, you got it all set up. So thank you for your time. Any questions?
Yes, if I understood right, you have like reserved space with an arm that will allow the user of the app to get in. Okay, so you are under the presumption that the person that has the app is using the carpooling. But what about a person saying that he collects another person and to use the parking because he doesn't want to go and find a parking?
Yeah, you cannot do that. So, so the way it works is we sort of take in all of the requests the day before, and we put into the algorithm. We get the groups. We form groups of carpooling, and the driver has to pick everyone up, and then they are allowed access to the parking lot. Everyone has to verify that they have been picked up. If not, they don't have access whatsoever. Yes.
So how about a person that wake up late and you don't pick him up because he's late when you arrive?
Okay,
so you don't have the parking then?
That is an edge case that we have thought about. So there's two sort of components to that. The first component is, what if the passenger didn't wake up, right? You as a driver, you show up to a person's house and then you wait for like 5 or 10 minutes and then no one shows up. Like, what are you gonna do, right? This person can't verify, so you don't have access to parking. The way we fix that is that after a set amount of time, you can sort of take this person out of your ride. But this only works if, one, you have verified that you have been there, which we can check because we have access to your location, and also a certain amount of time has passed so that we're also sure that you actually gave this person a chance to show up. After both of those requirements are met, then you can just sort of take them out of your ride, and then you can pick everyone else up, and then you're good to go. You also have access to your parking. However, if the driver is the one who doesn't show up, then that is an actual sort of risk to the system, if you will.
Okay, one more last question, I think. Okay.
Have you considered using, well, if they're going to be using phones, I imagine most of them are going to be Bluetooth and NFC enabled. Have you considered using those technologies, near field communication and Bluetooth, to verify the presence of the people in the car before actually allowing them in? Because it can just be spoofing like, hey, my friends, I send a request the day before to my friend, and I just say, yes, I am in the car. However, Bluetooth would allow for to check everybody's in the car, or like at least within nearness of one another before actually allowing. It's like, so you can't spoof the system. So,
so right now, everyone has to verify. So when you get to the actual location, right, there's, let's say like a 50-meter or so radius to where we check if that person is inside of that radius.
Okay.
And then if everyone verifies, then, that is that verification that we're doing. It's only location and that you're located close to the parking.
So the verification is not user, is the agent of verification is not the user. It's not like me as a user, I press a button that says yes. It's a location-based thing that's automatically done based on your location.
Both. So once you sort of press the button, that's when we verify if you're there or not.
Okay.
Yeah.
Yeah, that should allow. Yeah, great.
What else? Okay. How about a person that is willing to do carpooling but doesn't want you to have the location of the person? I don't want me to track me where I am, for example. How do you deal with that?
Okay. It's also not constant tracking. So the only sort of access that we have to your location is when you create a ride request, which you kind of have to give someone a location to pick you up. It doesn't have to be your specific location. It can also just be a location, right? You're not, when you request a ride and you're saying, I want to be picked up at this location, it doesn't have to necessarily be your actual phone's location, right? You can say, I want to be picked up at my house, but I'm not actually at my house right now. So you just send in like a Google pin, let's say. And the other use that we have for your location is when we're verifying that you're actually at the parking location so that we can give you access, which is more of a, it's more for the user, again, making sure that drivers are actually picking you up and also making sure that you're actually at the parking lot to actually give you access. So the only time that we actually need access to your location is, again, when you're verifying that you are at the parking lot.
Any other question? Thank you very much.
All right, awesome.
Our next presentation is Understanding Malware Obfuscation Techniques and Detection. The students are Jamie Santiago, Karina Lopez, Anthony Manzano, Arnaldo Maisonet, and Joshua Virreal.
Good afternoon, everyone. We are Team Maven, and we will be presenting our research project, Understanding Malware Obfuscation Techniques and Detection. Our MIT Lincoln Laboratory liaisons are Zachary Elobogan, Morgan Mango, Austin Tice, and Pedro Torres Carrasquillo, and our academic advisor is Dr. Naida Santiago. My name is Jamie Santiago, and I'm the project manager of this group. Here I'm joined by Karina Lopez, Anthony Manzano, Joshua Viriel, and Arnaldo Maisonet. The project description is as follows. Students learn about malware obfuscation techniques, current deobfuscation methods, and existing gaps in detection and analysis of deobfuscation tools. The project is divided into 2 parts: learning fundamental knowledge and skills in malware analysis, and learning obfuscation techniques, testing deobfuscation tools for effectiveness, and identifying any gaps presented in these tools. The goal for this project is for students to grasp the importance of understanding malware deobfuscation techniques in order to improve current deobfuscation tools that are crucial for strengthening malware detection, protecting our critical systems, and staying ahead of increasing cyber threats. The research objectives are as follows. First, we identify and categorize various malware obfuscation techniques. Then we analyze the effectiveness of different obfuscation methods in evading detection. We evaluate the limitations of existing deobfuscation tools and propose potential improvements to deobfuscation tools and techniques. The technologies utilized for this project is FlareVM, which is a sandbox where we do our testing of the malware. Our sandbox is hosted in a Proxmox server, and all of our code and write-ups are hosted in our GitHub, and we utilize Ghidra, which is an open source tool for reverse engineering. Moving on to the background.
So, what is malware? Malware refers to any software intentionally designed to cause damage to a computer, server, client, or a network of computers. Malware can take the form of scripts, code, and other types of software. We have a depiction of different types of malware, but we focus on ransomware. Ransomware blocks access to your data or even to your computer until a ransom is paid.
Now, there are 2 types of ways to analyze malware. It's going to be static and dynamic analysis. For the focus of this research, we focused on static analysis, which is where you analyze the code of the malware. Now, what happens when you don't have access to the source code of the malware and you can't read it? That's where reverse engineering comes in. Reverse engineering is when you take a malware binary and you go ahead and put it on a reverse engineering software such as Ghidra, and it can go ahead and decompile the binary instructions into assembly code. And then Ghidra has the option of taking this assembly code and generating C code out of it, which is more human readable, and it's easier to understand when doing reverse engineering analysis.
Moving on to the methodology of this project. First, we start with the selection of our malware type, that being ransomware. Then we move into our sample acquisition and selection of plugins. For our third step, we do literature review on these samples that we acquired and our selection of plugins. Then we evaluate these plugins on our samples, and then we provide an analysis on the findings from these plugins.
For our literature review, we started by researching about malware obfuscation. So obfuscation itself is the process of transforming readable code into a version that is intentionally hard to understand. Key techniques are compression, encryption, which you can see here in this image, polymorphism, which is when the code changes its appearance with a new encryption key each time, and metamorphism, which is when the code changes appearance each time but keeps its functionality.
Moving on to malwares utilized, we first have WannaCry. It spread in May of 2017, and it exploited a vulnerability called Eternal Blue, which was based in old Windows versions. Eternal Blue allowed remote access to your computer, and the malware was able to download itself without your permission. WannaCry also had the properties not only of a ransomware, but also of a worm, which means when it infected a computer, it scanned the network, and if other computers had the same vulnerability, it also infected them. It also encrypts files on the PC's hard drive. We also have Petya. It was discovered in 2016. It also infected Windows-based systems. It also used the Eternal Blue vulnerability, and it spread mostly through email attachments. And we also have Satana, which was first identified in 2016. It spread through phishing emails, and it not only encrypts your data, but it also blocked access to your computer. And it was designed to silently infiltrate computers and encrypt various files.
In the fourth malware, we have Thanos. Thanos started appearing in late 2019, and it used the RI place obfuscation technique. What it do, RI place, is that exploit how Windows handle the renamed files, and with that it creates multiple encryptions of the affected file. And it's a ransomware as a service. That means that this malware specifically has been sold to other hackers to use it. Moving on, we got now Lucky. It was first seen in 2016, and it has both properties of a ransomware and a virus. This type of ransomware encrypts and infects networks via Microsoft Word documents or files. And the last ransomware we analyze is Mamba. Mamba has the ability to encrypt your entire system using Descriptor. Descriptor is an open source tool that allows you to encrypt your entire device. And it also uses PSCEC that allows administrator to manage your device from remote locations.
Now for Ghidra and Ghidra plugins, as mentioned before, Ghidra is an open source reverse engineering tool developed by the NSA, and Ghidra plugins extend its capabilities by automating tasks, detecting patterns, and aiding analysis of obfuscated or encrypted malware. The plugins we used for our analysis are Lazy Ghidra, Obfuscation Detection, FindCrypt, PyFindCrypt, Ghidra Strict by AllSafe, and Instruction Overlapping, which will be further expanded by Anthony. For our results, in the first table we can see the obfuscation techniques we were able to find in the samples. In Thanos, we were able to find dead code insertion, packing, and encryption. In WannaCry, we were able to find packing and encryption. In Mamba and Satana, we were able to find encryption. In Locky, we were able to find dead code insertion, packing, and encryption. And in Petya, we were able to find packing and encryption.
Now in this slide, we can see the type of obfuscations that were actually detected by the tools that we use in the scripts. Lazy Ghidra was good finding buffer overflows, but for the purposes of this research, that is out of scope. Obfuscation detection imprinted statistics on the functions of the malware. It go ahead and generated statistics on the average instructions per function. If any function were on site on these average instructions, maybe you could deduce that something more was going on in that function that had to do with the actual malware. FindCrypt actually found cryptographic constants and pointed to the functions that were using it. This is really useful to find the functions that are actually encrypting the system and what type of encryption it is using. Ghidra script detected dead code insertion. This is when you put code that actually does nothing for the program. It's just there as dummy code, and this makes it harder for reverse engineers, since you can be looking at the compiled C code that provides no functionality or whatsoever to the malware, making it harder to analyze. Then instruction overlapping did not find anything on the methods that we were looking for, but it did find a method that we didn't think of, which was the actual instruction overlapping. This is when you take a certain instruction and write it after a certain amount of bytes, variable length. And if you offset this instruction by a certain amount of bytes, you can actually generate new instructions. The CPU only understands binary. So if it receives a valid set of ones and zeros that it can execute an instruction that when disassembled is not present in the reverse engineered code. The areas that are not filled right now are areas of improvement, or we can develop new scripts to go ahead and detect these types of obfuscation techniques, such as metamorphism.
In conclusion, student learns to analyze obfuscation technique through scripting and plugin evaluations, gaining practical experience in identifying and classifying patterns used by real-world ransomware samples. While plugins were effective in detecting common techniques such as packing, encryption, and dead code insertion, advanced methods like metamorphins and control flow flattening proved more difficult to detect, highlighting the limitation of static analysis and the need for more sophisticated tools.
The areas that we can focus on for future work is editing the obfuscation detection script, because right now it only detects the statistics for the entry function and the main function, which is when the malware is first called. If we can do this for each of the functions in the system, it'll provide more statistics and more in-depth analysis of the malware. We can develop obfuscation scripts for detecting metaformism. Right now, we didn't find anything that could detect when the malware was rewriting itself or changing instructions. And this is very important because this can generate new signatures per malware, even though it is the same malware. And we can also improve the scripts to run automatically. We can run a master script that can detect some type of obfuscation and then call other scripts to go ahead and do a more in-depth analysis of that function or obfuscation technique that is going on.
First, I would like to express our gratitude to our academic advisor and MIT Lincoln Lab mentors. Thank you for your expertise, and that is all from us. Any questions?
Hey, good job, team. I'm just curious, you're managing malware. What what did you do to, prevent the propagation of this malware in the university's network system? What kind of precautions did you take?
Well, the sandbox that we utilize is not connected to the network itself. It has various firewalls in place to ensure that it doesn't propagate through our university network. And we also do not run the malware. We strictly perform static analysis, so we only look at the code structure.
Okay, so there's no actual code running?
There is no code running.
Awesome, okay. And so you mentioned that you're interested in sort of doing some further development into, some of the methods of obfuscation that there aren't really any tooling for. Have you found out in the wild any research or sort of, ideas of how to develop these tools that you can use for your future work?
Yes, I have stumbled upon some research papers on developing tools for metamorphism, and I think that is something that we could dive into for our future plans of the project.
Thank you.
Hello. Do you have any statistics of false positive or positive false in your tests, or do you always have a malware to detect?
Can you repeat the question?
I mean, do you, in your experiments, do you have any statistics of false positive that you have a malware you don't detect, or positive false, you don't have a malware but you detect that something is there?
So we do not have any statistics for that. We strictly test the plugins on the 6 samples that we acquire for malware. So these plugins, the techniques that they found are strictly on those files of malware.
So all your tests, you know beforehand that there is something in there.
Yes, we know that our files, the files that we are testing, we know that they are malware.
Any more questions? Thank you.
Thank you.
Okay, we are right on the spot with the agenda. At this time, we will have a break. There is some snacks in the cafeteria area in the Tarzan's room. So let's join there and come back here 10 to 4.
disconnect them.
Pregunta, ¿la laptop se apagó? No, Windows P, maybe? Windows R. Espérate un segundo. ¿Sabes un segundito? Duplicate. ¿Qué cambió el display? No quiero mostrar eso aquí. No, es que se cambió acá y estoy dando de...
¿Cómo que se cambió?
Ah, ahora quería regresar. Ok, estamos aquí, estamos. No sé qué pasa aquí de momento. Se apagó. Ok, no está saliendo, voy a cambiarlo de...
No importa si yo acabo de salir de ahí.
Pero uno se debe conectar a la otra computadora, pero aquí no está...
Si no está, no significa que no lo leyó. Léelo acá. Sí, pero tu computadora no tiene un amplificador como este. No lo está leyendo.
Claro, porque lo había intentado... ¿Puedo enviarla por email?
Usa tu computadora y me lo grabas aquí.
Sí, es que fue con la computadora de otros compañeros porque lo traía por aquí.
We have technical difficulties, so give us a couple of minutes. Mándamelo por email, no creo, si yo puedo.
¿El email de Raúl? ¿O cuál? ¿IAP? Ok. ¿Qué por una razón no lo quieres? No, sí, connect. Ah, mira, harta. Harta. Pero no sé si eso es. Sí, está ahí. ¿Logramos resolver? ¿Quién comenzó? Yo.
¿Las fotos dónde están?
Comienza a hacer un poquito más.
Good afternoon again. This is the last session of the afternoon. Our next presentation is reduction of power consumption during training for machine learning models. The students are Etienne Michael Capella, Edwin Almodóvar, Raquel Quiñones, Jadiel Montero, Yomar Vélez, Giovanni Roban, and Sebastián Isegui.
Good afternoon, everyone. We are Panda Hat Adversarial, and we will be explaining the reduction of power consumption during training for machine learning models. This is our team, as we can see. And before we begin, it's helpful to clarify that we have two groups in this team. Group one is tasked with understanding the main objective, which is investigating power consumption during machine learning training. With this, we experiment on different machine learning models. And as for our other group that is tasked with understanding the foundations of machine learning, they will slowly integrate into the group once they get more knowledge. They use tasks to understand better the fundamentals of machine learning, and they will begin with a brief explanation of what machine learning is to understand our main objective better.
So let's start with what is machine learning. So machine learning is a way of teaching computers to learn from examples instead of instructions. So what we do is we feed the models with data sets where the machine recognizes patterns and makes decisions and predictions based on those patterns. There's different machine learning architecture, but for this research, we're focused on neural networks, which these are designed to mimic the way our brain works. So this consists of interconnected nodes or neurons organized in different layers. So the layers consist of like the initial layer, which is the input layer, which receives the data. Then we have the hidden layers, which process the data, and then the output layer, which generates predictions. In the left image, we can see a simple neural network, which one hidden layer, and in the right image, we can see a deep neural network which has multiple hidden layers, which allows the model to learn more complex patterns. Going a bit deeper into neural networks, we're going to talk about the convolutional neural networks, or CNNs. These are designed to process image, and how they work is that instead of processing the entire image at once, it uses something called the kernel, which is a small matrix that goes over the image, processing it section by section. In the image shown here, we begin with an image of a zebra. The kernel then moves across the zebra, creating feature maps to collect or capture important features or information. Then we do pooling, where the size is reduced, but still the essential information of the image is still contained. Finally, at the end of the neural network, we flatten the image and then pass it to fully connected layers. This then classifies the image on the extracted features, and on this case, we can see that the image or the model has a 70% confidence that this image is a zebra. So this process is very important and makes CNNs excel at image processing. Now I'm going to be leaving you with Sebastian, who will be going over the analysis.
After we made both the AI training modules, we analyzed that neural networks are good at understanding nonlinear relationships and have a really flexible architecture allowing for easy augmentation in order to get better results. But they do require a lot of data and a lot of tuning in order to prevent overfitting. Convolutional neural networks are good at capturing spatial features and patterns in image data sets, which allows for easy classification. They also require large data sets, and their energy efficiency can vary depending on the techniques used in the convolutional layer, because there's padding, max pulling, and different types of strides. They can overfit easily in small data sets. Below, we have the most pertinent features and results from the training modules, and they are a binary classification.
Here are some images from our models that we trained. On the top left, we have an image of the image, which was applied a color map so that we could highlight the areas which have the most condensed amount of vegetation. On the second image, on the top row, we can see the ground truth or the labels which the model is supposed to predict. And on the right, we have the predictions that the models made. We can see that it could capture the areas which had the most condensed amount of vegetation. On the bottom row, we have images from the convolutional neural network, and the bottom left one contains the ground truth, same as the neural network model, which were the top images, and the right image has the predictions of the model. We can see that the yellow parts are the vegetation, and the bluish parts are the things that are not vegetation. And the model was able to get the condensed parts of the vegetation, but it wasn't very good at detecting the edges.
Group 2 utilized key visualizations to evaluate the performance of our models. As you can see on the left-hand side, we use a epoch versus loss graph. Through this visualization, we can see how well our model is being trained over time. In this specific scenario, we can see that the loss quickly decreases and stabilizes at the bottom. Through this, we know that our model is learning correctly and there is no overfitting. On the right-hand side, we have a confusion matrix. With this visualization, we can see the actual values and the predicted values and see how well our model distinguishes between plants that are alive or plants that are not alive. Through these visualizations and others, we can make adjustments to our models and improve their performance.
So moving on to our qualitative insights, our models were able to distinguish between different land masses, but struggled with sparsely vegetated areas. The multi-class model we implemented showed rough edge transitions between vegetation health levels. We also enhanced the performance of our models using data augmentation techniques, such as scaling, rotation, and flipping. For our evaluation criteria, we evaluated the results we obtained by comparing them against human baselines and published scientific papers. We also reflected on our learning outcomes and the hands-on experience we gained.
Now that we have a good understanding about machine learning and our background, it's time we address our problem. Training models is a very energy-intensive task, which raises concerns about the sustainability of this practice. Not only that means training is very expensive. For this reason, we focus on optimizing energy consumption during training, specifically into CNNs. Our hypothesis is that low-rank adaptation can reduce training time and consumption and even open up the door for more accessible, larger-scale models. Additionally, by applying a comparative stopping criteria, we can streamline the training process to multiple model variants and reduce unnecessary training. So our principal objectives are to create an efficient machine learning training framework, utilizing the aforementioned stopping criteria with defender comparison and LoRa application to CNNs to reduce training time, which will be shown shortly. To then evaluate power consumption by benchmarking training time across the optimizations.
So as for how we set up our experiments, we begin with a pre-trained resonant 18 model. We're performing object classification tasks, by the way. What we do is that we train and test with the CFAR 10 and CFAR 100 datasets, and then we evaluate this model performance. We are integrating LoRa on specific layers, such as the linear and convolutional 2D layers, and we focus on fine-tuning these specific layers. We also train with specific epochs and resources to simulate difficult scenarios. We implement the defender baseline comparison, a stopping criteria tailored for models addressing similar problems, and we evaluate primarily training time and epochs, as well as we also have the secondary metrics, which are accuracy and testing sets. We also assess the overfitting of these models. For the low-rank adaptation, this technique is first, you take the model and you freeze its original weights, and then you insert low-rank matrices, which are matrices that approximate the weights of this layer. During this experiment, we applied this and in specific layers, such as the internal convolutional layers and the fully connected layers.
So now we're going to talk about defender-based stopping criteria. There are three key parts for this technique. First, is patience, which is the amount of leniency that we allow to pass before we start evaluating. This is important because not every model learns or behaves the same way. For example, a model might learn slow at the start and then start to snowball and learn faster as it goes. So this is very important to adjust to different types of models. It's also very important to have a performance threshold, which is how much do we allow for the model to perform and accept it. In our case, we use 2.5%. We also have the key part, which is defender candidates, which essentially is we train a model to completion, and that becomes our defender. And then we compare each model, subsequent model that we have, to that defender. If the model, after a certain patience level, starts to perform, to a lower degree, we stop training it. The idea is if that model is no longer, fruitful, why even start training it anymore? Just stop it. In short, the idea is to compare a currently trained model with the best performing model yet to deem whether this model is worth continuing. But it's very important that all the models that we select for this criteria are tackling the same problem. In other words, they must be the same domain. For example, if we're tackling vegetation, you're classifying vegetation, all of the models must be handling that task. But they can vary in architecture and hyperparameters. Now let's talk about the results of both techniques. For LoRa, we applied it, as my partner mentioned, in linear layers and the convolutional layers. Initially, we started with the Cypher 10, which has a lot more data. For each class, it has around 6,000 images. So it took around 46 minutes to have an accuracy around 90%. Compared to training from scratch, to reach around 84%, it took around 3 hours. So it's a great reduction in training time. For Model 2, we used Cypher 100, which is 600 images per class, which means there's a lot less data. And in this case, we see that the model doesn't perform as well as the others, which is a 68%. Then for the Model 3, we applied data augmentation. And we could see that the model went up in performance around 5% in the classification. So that means that in this case, the model was having issues with overfitting. And then for stopping criteria, we noticed that when we applied it, we have a reduction of around 50% in the base models. The models training from scratch, I should specify. This is because basically after the Epoch 10, which is where I identified the sweet spot, if it went past that and the performance was much lesser than 2.5% compared to the other one, we just stopped training, which managed to reduce around a total training time of let's say 5 hours. It reduced it to 3, which has been proven to be an efficient technique, especially when you're playing around with changing the parameters.
As for the data analysis, we found that LoRa reduced training time, but in terms of overfitting, we did find that they overfitted in both models, more so on the CFAR 100. This was because of certain reasons, which was the mismatch of both ResNet and CFAR. There was also not enough data per classes, and when we applied this meant that we had to apply regularization techniques, dropout layers, and data augmentation to prevent that overfitting. For the performance gains, we found that LoRa did speed up training and did achieve better results, but only when the data is sufficient. And the data augmentation improved the CFAR 100 training by roughly 5%. For our next steps and future work, we will be trying to evaluate novel variations of this technique with CNN architectures, and we will be experimenting with different techniques such as different rank values and scaling factors. We will also try to implement more integration beyond the layers that we targeted. Additionally, we will want to implement these findings into adversarial machine learning, since we want to reduce the computational power when using adversarial training. For Group 2, they will be conducting comprehensive literature review and finding articles relating to the vulnerabilities of different machine learning models. Once they gain that literature review insight, they will be joining Group 1.
So, for conclusions, Group 1 managed to implement LoRa successfully on difficult scenarios across the board, across different various datasets and architectures. We managed to significantly reduce training time and consequently power consumption. It is important to remind you all that we applied this on a very difficult case. Again, the model mismatch. We also aim to continue contributing by applying into adversarial machine learning, which is an unexplored area when it comes to LoRa. Group 2 has strengthened their machine learning fundamentals through their series of tasks, which dealt with data preprocessing, modeling, training, and evaluation, and data augmentation. Applying these into the real-world problems through their analysis of vegetation and land classification. Before we finish, I want to give special thanks to Nadia Santiago and Alcebiades, which is not here, but also Shaya Katihar, Luis Romero, and Jose Martinez and Pedro Torres, which were our advisors throughout this investigation. Thank you. Any questions?
You mentioned a reduction on training. Do you use exact sample data for training, or do you use different training data sets?
Yeah, we used specifically 2 training data sets, which is Cypher 10, which is like 10 classes, and for each class, 6,000 images. And we used Cypher 100, which is 600 images per class, which is 100 classes.
And you saw the reduction in both?
Yeah. In our case for Cypher 100, we had some overfitting because, when we go into the classes, 600 images is very little. And especially in the situation that we put the model into, which is like we're using a very small image, and the pre-trained model is used for a larger image. So it's, it's struggling to try to keep up, which is like for a Cypher 100, the performance, the highest it got was 74%.
Any other question? Thank you very much.
Thank you all.
Our next and last presentation is Portable Guiding Vehicle for Visually Impaired, a compact, reliable, and user-friendly solution. The students that were the project are Juan Hernandez, Abner Perez, Rebecca Rivera, and Victor Fernandez. All of those 4, 3 of them already graduates, and the only Victor Fernandez is here, are going to be presenting the project.
Good afternoon. My name is Victor Fernandez, and today I'll be presenting the capstone project titled Portable Guiding Track Vehicle for the Visually Impaired, a compact, reliable, and user-friendly solution, which I was involved in as a research assistant. To begin, the project's main motivation was to provide a training method for blind runners without the use of a guide, as in a person who the blind person holds on to and runs alongside them. The client in this case wanted this device so that they wouldn't have to depend on such a guide, because in this case they found the guide too slow. And so the equipment is based in this case on 3 systems: optical, distance, and sound. and this presentation will cover the constraints, the budget analysis, and related projections for each of these systems. Now we will look at the technical documentation of each system with their associated constraints. In these images, you can see the purchased vehicle that was used to sort of start the development of the custom vehicle, and you can also see a more detailed schematic with the associated parts, which we will see more of shortly. For the optical system, a Pixie 2.1 camera was used with the initial vector detection method, which did not work due to accuracy issues related to the lane width. As in, the camera, if the running lane was too close, the camera using the vector system would get too confused and wouldn't register it correctly. As a solution, a color detection algorithm was implemented, calibrated under various lighting conditions. Here you can see several signatures, so to speak, belonging to lighting types that impact the visual image of what the camera detects. The table shows various types of twilight and sunrise/sunset for these signatures. In essence, these signatures are like values for the color detection system so that it knows which specific shades to look for as the time of day changes. Because obviously, an environment doesn't look the same depending on what time of day it is. And so we have to give it these signatures corresponding to different times of day, different types of twilight, so that it recognizes them and acts accordingly. Continuing with the camera, the operation focuses on identifying the largest white block, because in this case the running lanes have these white parts to them, and sending its position on the horizontal axis to the microcontroller, which then adjusts the steering angle with a proportional control algorithm. Tracking is reliable on textured floors after testing and under different lighting conditions due to the lighting signatures, which I mentioned, the latter being aided by an LED that mitigates noise under unfavorable conditions. This is an LED that was installed on the vehicle so that in cases of poor lighting conditions, it could be left on to aid in the detection of the running lane. Here is a table showing different tests using the vector detection method. As you can see, detection is compromised in the case of multiple objects and in the case of a line close to the camera. This is the vector detection system. So in the case of both multiple obstacles around the running lane and the case of a lane that is too close to the camera, this vector detection system does not work as intended. And so, as I mentioned earlier, that's why the group moved to the color detection system. Here, the color detection test. These tests were conducted using the color detection method, which can identify the lane's color in all scenarios, whether using a solid color, similar colors in the surrounding area, floors with textures to them, irregular textures, not just a flat floor, or different lighting conditions. For this last test, although the calibration process is not affected, like I mentioned, keeping the aforementioned LED on at all times is mentioned as an alternative. Here are the variables involved in implementing the steering control system, along with more details regarding the servo angle. For proportional control, the position and threshold variables represent the horizontal position of the block and the center of the camera's field of view, respectively. This slide shows the real-time behavior of the lane following system. Precise adjustments for off-center blocks are also available. Now we move on to the distance system, the goal of which was to maintain an appropriate distance between the vehicle and the runner. This system initially relied on a Wi-Fi or Bluetooth signal, but due to sensitivity and accuracy issues, it was switched to an ultrasonic sensor. Here is the sensor in question with an analog output to calculate the distance. The calculated distance is then used in a function called map. To be more specific, the map function performs range conversions. This is used to change the resolution on the ESP32 from 1024 to 255 and send the pulse width modulation, or PWM, to the operator to control the DC motor being used. The motor driver, seen in the image, handles peak currents of up to 30 amps for the motor and input voltages of 5.5 to 16 volts. It has output voltages ranging from 3.3 to 5 volts, with the latter being unsuitable for operation. In terms of the sound system, its purpose is to provide auditory guidance for the runner from the vehicle. The sound characteristics used to represent the different scenarios, in this case the chosen sounds for different situations that the runner may face or that the vehicle may encounter, are an alternating frequency beep for a straight lane, a higher frequency beep for curves, and a continuous beep in the case of obstacle detection in the running lane. Continuing with the sound system, its components are an 8-ohm speaker and an amplifier. The amplifier, in this case the Max 98357, was chosen due to its availability and space constraints for the system being developed. Here you can see a flow chart showing the general operation of the sound system. There are different behavior options depending on the type of lane, like I mentioned, the presence of an obstacle, and there's also an implemented function for whether or not there is enough battery remaining. If there's low battery, there's also a behavior that accounts for that in the sound system design. For the sound system test, the right hand lane and curve test were conducted with the straight lane and curve test performing as expected. The obstacle test was not completed, and future improvements include adjustable volume and improvements to the dynamic environment. Here you can see a system integration by schematic and also PCB, or programmable control board. This is the one that was developed for the purposes of prototyping this system. This is the aspect that the additional functionality of an emergency shutdown. In this case, it would just be a sort of kill switch that if the vehicle was to encounter a serious issue or started malfunctioning, a signal would be sent to the device so that it would shut down completely and not cause potential accidents. In this case, 2 microcontrollers were used for the development of the prototype. In this case, the ESP32 room would act as the emergency button, so you would press the button on the room and it would send the signal of the button being pressed via Wi-Fi, and then an ESP32 S3 model would receive that data and then act accordingly. Now I will move on to non-technical constraints. The restrictions mentioned include delays, the need for further testing for user safety, and potential legal risks due to failure or collision. The product's potential impact on society and the market could include advances in rehabilitation technology, ADA compliance, and improved accessibility with potential economic benefits. Now I will talk a little bit about the project budget. Here's the first cost analysis, taking into account the materials or components used. Based on this estimate, with 39 units sold per year and a cost of around $975 per unit, the estimated profit after 6 years is around $101,000. I should stress this is a pretty specific estimate that was done, but nonetheless, I included here for posterity. And so this is a second scenario, adding additional cost of development, such as 3D printing and power supplies. And so within a similar scenario, there is also a gain of around $81,000, but I should stress some of these costs will probably multiply, such as working and also power supply inventory. Now I will show some conclusions from the group and some future work possibilities. Possible next steps include functionality, achieving integration of the 3 systems, and general system improvements, such as reliability, security, features, autonomy, and accessibility. Future potential includes transforming the experience for more people who need it and exploring broader accessibility technologies. And here I provide some references and bibliography. Thank you very much.
I have a question. When you were talking about the sensors at the beginning that you were measuring distance, you mentioned that you were using Bluetooth and you were using Wi-Fi. However, that didn't work and you switched to another type of sensor. So can you explain a little bit what happened?
Yeah, I think it was basically due to, because this is a device that is being used outdoors, there could be issues with noise interference, with Wi-Fi, with a running track. This kind of environment could cause issues when it comes to like Wi-Fi access points and also Bluetooth. So I think it was just a matter of testing and then just moving on due to unacceptable variations in what was needed based on the usage of Bluetooth and Wi-Fi. I believe it was just not enough for what was needed for this system.
A couple of questions. You mentioned that the feedback that is given to the runner is an audible signal. Is that right?
Yes.
And you have a speaker mounted on the car, or is?
Yes, it is in the vehicle.
Have you considered providing an individualized signal to the runner in case you have multiple runners running simultaneously?
Can you repeat the question?
Yes. Imagine the scenario where you have several runners
Yes.
using the same guidance system. If you have an audible signal that everyone can hear, there might be confusion in the tracks, right?
Yes.
So the question is, have you considered using an individualized signal for each runner so that there cannot be that kind of confusion?
That is definitely something that could be implemented, a specific or adjustable sound for each vehicle speaker so that each person recognizes their specific sound to their vehicle. That's something that could be implemented and provide variation if it came to a scenario of commercializing the product.
Okay, he's answering by his memory, but that wasn't his part. The student that developed the audio system, what he said is that he shows the constant beep, the sound, the constant sound for the obstacle, because that will be a risk for anybody in the track. I mean, you have to stop the race if something is on the track, no matter in which part of the track is. But it will change the frequency, the beeping frequency. It will be changing depending on if you have more than one runner. So one runner will hear like a small beep, 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 another one beep, 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 beep. So by using the frequencies, you can differentiate that, which is your car.
Okay, so I would like a little clarification first. You're using the ultrasonic sensor to basically keep the, let's say, the car in front of the person consistently at a specific distance, right? So so when it fails, for example, let's say the user starts going a little bit to the left, to the right, because that can happen. Is it still accurate, or are you using like an array of ultrasonic sensors to try to maintain, a comprehensive like view of everything?
This was, I believe it was chosen just based on testing. It was a chosen model, and also within the constraints of the course, I believe it was the clearest option available to the person that developed this system. Again, I focused on the emergency shutdown system. And so, yeah, I believe it was just chosen based on what was available at the time, the constraints, and what was required so that the person involved in that system could develop their aspect and integrate it with the other systems.
Right, perfect. One last question. I like the idea of the emergency shutdown, but I also want to ask, have you thought about, the team have they thought about what happens if the user is to fall, something happens to the user? Have you taken those considerations of how could I help them?
That is a scenario that could be explored. It would, I think, involve a lot more, a lot of upgrades to the system, because that way the system would need to recognize the shape of the person as they fall, not just a general person running. That's a general shape that you can maintain and that you can just have the system recognizing that on its own. But then if you have the person falling, I guess you could just have if this general shape that's being recognized by the camera isn't present anymore, that could also be mixed in with the emergency shutdown. So that way, let's say if the distance system doesn't recognize the shape of the person that's supposed to be the runner, then that way there could be sort of like an alarm system or added functionality for the emergency shutdown.
Thank you.
I just want to answer his first question. His first question, it was a limitation. Like if you want to have multiple runners at the same time, the car will follow one line. You won't stay in a lane. You will be running on top of the line, and you cannot have any runner to the next two lines, because if you do, they might be interference when runners are coming through. Yeah, that was a limitation. And another limitation that he didn't mention is that these motors, because this is high-speed car, they have up to 30 amperes, depending on the velocity of the person. So it will create an interference with the circuitry that was on board, and that was part of the problem with the communication. So those issues are not resolved. The car is still in the lab. We haven't delivered it to the user.
Hi, yes, interesting project. I wanted to ask whether you took, talking about limitations, whether you took in consideration the range that the runner goes through. It may be like 10K, marathon, Ironman, and did you take like in consideration the battery that this device has, and what ranges the hour that ranges this device?
Yes, I believe for the client, the types of events that they were participating in, I believe this person was a competitive runner, but was now simply doing it for leisure or practice, I should say. But I think the vehicle that was bought, I think the battery life was sufficient for whatever type of usual routine this person had. I don't think it was anything like a marathon. I believe it was stuff that you could do on a track normally. I believe the battery life was sufficient.
This is very client dependent. The client do train as a long distance outside a track, but it need a guide, because in the street you will have more obstacles. You can have steps and other stuff that you won't have in the track. But he asked for the car specifically for the track. So we developed the solution that he asked. and the life of the battery is about 20 minutes. So that's enough for him. Any more questions? Thank you very much. I would like to thank our viewers in the YouTube channel. We reach about 260 viewers during the day. At least the very short time that I was there, we reached up to 11 viewers at the same time, so that's a good number. I know that there are some companies that saw the presentations through the web because they couldn't travel to Puerto Rico. They didn't have the authorization. So I would like to thank them because they stayed with us the whole day. Also, this was the last presentation. We will come back tomorrow. We will start at 8 o'clock sharp. By the end of 1 o'clock, we will have one more last presentation after lunch, and that's it. At the end, we are going to meet with virtually or in person with the companies that are here. For only the companies. So I would like to thank you all the students. You have done very good work. I also would like to invite you. There is still some snacks. We need to clean up the room because there is another activity. So if you have a hungry roommate, please take more than you can eat and share it with your friends. So I will see you then at the Tarzan room, and hopefully you will be satisfied with your choices of food. Have a good evening.